Hello? Wow. Okay, great. So good morning, everyone. Hope you had a good weekend. And this morning we're going to get started talking about how magnetic fields in stars are generated and their importance. And we have Matthias Rempel. Matthias is here at UCAR, and he received his PhD in 2001 from the Kiepenheuer Institute for Solar Physics in Freiburg and the Max Planck Institute in Kapfenberg-Lindau with Manfred Schussler. He then came to the US with a postdoc first and then as a staff scientist, and has been here ever since. Apparently you enjoy Boulder very much. Anyway, I'll leave it over to you, Matthias. Thanks.
Okay, can you hear me okay? Okay, good. So this morning I would like to talk with you about the processes which lead to the creation and destruction of magnetic fields in the universe. And I have two lectures. The first one is a little bit more equation heavy. That's the reason why it's a LaTeX generated PDF. So I hope I don't overload you with that, because I mean, I have to get some fundamentals of dynamo theory through here, and that's hard to do without equations. The second presentation is more about applications to the sun, to other stars, to the geodynamo, and that one has very few equations. So I hope just bear with me through the first lecture here. Okay, so see, okay. So the scope of these lectures is really introducing the general concepts of dynamo theory. So I would like to give a brief introduction about magnetic fields in the universe. What do we know of magnetic fields at different scales? A very brief review of MHD and the induction equation. You had already a lecture about MHD, so this is just a few slides reviewing a few essentials we need for these lectures. And then I will make some few general remarks and definitions about what we consider a dynamo in the astrophysical context. I will talk about a few specific types of dynamos, small scale, large scale dynamos, introduce mean field theory, which is a formalism, how to essentially model the large scale component of the fields by averaging over smaller scale components. And then finish here with a few concluding remarks. And then, as I said, the second lecture will be much more about applications. So let's talk a little bit about magnetic fields in the universe. Of course, the one body we know the best is the Earth. It has about a field of 0.5 Gauss. And that it's around 0.5 Gauss is not a coincidence. Carl Friedrich Gauss, he invented the unit Gauss to be kind of a meaningful measurement of the Earth's magnetic field. That's the reason why it's of order 1 in that unit. We do know that the Earth had a magnetic field for a couple billion years. And the way we know this is essentially when you have volcanic rock deposits. The magma is too hot, it cannot be magnetized because it's above the Curie temperature. And then when lava cools down, it kind of freezes in the magnetic orientation which was present at the time. Particularly if you look at locations like, I mean, the ridge in the center of the Atlantic Oceans where the plates kind of depart from each other, you kind of have a steady record of magma deposits, which kind of give you a record of the history of Earth's magnetism. And for that, we know that the Earth had a field on the order of this magnitude for a pretty long time. And this is much longer than the ohmic decay time scale, which is more something like 10,000 years for the Earth. And it has also strong variability on shorter time scales, as short as 1,000 years, which kind of suggests there must be some dynamic process maintaining this field. And also many other planets and moons in our planetary system do have large-scale magnetic fields. In the case of the sun, we have magnetic fields from the smallest observable scales, and that is kind of something on the order of 100 kilometers and maybe a little bit less to the full scale of the sun. The large scale part of this field has a fairly regular 20-year cycle. Now, the ohmic decay time scale in the case of the sun, if you really use the plasma resistivity, would be something like 1 billion years. So you could kind of argue maybe there's some leftover from the origin when the sun formed about 5 billion years ago. But of course, it's only such a long time scale in the absence of turbulence, and we'll touch on this later. And then we have observations of other stars, and stars with outer convection zones. They have very similar magnetism to the sun. different strengths. If you have faster rotating stars, they tend to have stronger fields. Other stars also have cycles. It depends a little bit on where the stars are on their rotational track, what the cycles are, and I will come to this back in the second lecture. There are also stars which have outer radiation zones. There it's possible that since they don't have turbulence, that there may be some magnetic field left from the formation process of these stars. And of course, the stars with outer radiation zones, they have a much shorter lifetime. So it's completely possible that after a few million, 100 million years, there's still some field left over from their formation process, but they do have likely active field generation in their convective core. And then even if you go to the scale of galaxies, there is field on the order of a few microgauss, and the field structure seems to be coupled with the matter distribution in the galaxy. So talking a little bit more about specifics, if you look at the sun, at the Earth, this is a map of the magnetic field of the Earth, and red and blue here indicate the different polarities. So the dominant field is a dipole, but it has some distortion. So it's actually a superposition of several multipoles, but dipole and quadrupole are the two dominant ones. And the magnetic field also has a shorter term variation. Perhaps the most significant one around this time is that actually the North Pole is moving from northern Canada over towards the direction of Russia. And it's kind of at a rate of something like 40 kilometers per year. So that gives you something like 1 millimeter a second. And that is believed to be roughly the flow speed of convective flows in the outer liquid core, iron core of the Earth. And looking at this magnetic field longer term, actually the sun, the Earth had some field variations more on a random scale. A given polarity is present for something on the order of a few 100,000 years. Currently the sun, sorry, I always mix it up. The Earth had its field, the current polarity we have for about 800,000 years. But if you look in these records, you have switches of the polarity on rather short timescales of about 1,000 years. And even if you are within a phase of a given polarity, there are strong variations of the dipole moment. There are even some indications where there were some attempted reversals which really didn't make a full reversal. So the magnetic field is actually very dynamic on longer timescales. And if you go even longer in the past, there have been even phases where the Earth seemed to have kept the same polarity for much longer timescales, something like 100 million years, and that may have been related to some changes in the core mantle boundary condition due to plate tectonics and convection in the mantle of the Earth. When we look at the sun, this is a magnetogram from SDO-HMI. You see everywhere these very small scale fields, and I will talk more about this later, which is really salt and pepper mixed down to the smaller scales we can observe. But if you look at the larger scale fields, we do have the sunspots with up to 4 kilogauss field strength. So that's something like 8,000 times the strength of the Earth's magnetic field. And these strong field concentrations, they also have preferred polarity. So if you, for example, look here, northern hemisphere, you have always a negative polarity here on the right side. If you go to the southern hemisphere, it's the other way around. And if you look 11 years later, then this switches. So there are these large-scale polarity rules which suggest it's a process which really feels the full scale of the system. And this magnetic field comes in cycles of about 11 years. So if you look the full cycle, of course, with polarity flip, it's 22 years. Most of these active regions show up in low latitudes. Early in the cycle, around 30 degrees, later in the cycle, close to the equator, which leads to this butterfly diagram, which is just a plot of sunspot positions versus time. This is not a motion of an individual sunspot. It's just that sunspots, they typically live something on the order of a few weeks. Some in extreme cases, they can live more than a month. But for the most part, sunspots appear early in the cycle in high latitudes and later in the cycle close to the equator. The strength of the cycle varies with time. by a moderate amount, something like a factor of 2. But if you look much further back in time, there have been phases where the sun had much lower activity levels, which are called grand minimum episodes. Like shown here, the most famous one is the Maunder minimum around 1650 to 1700, where sunspots were mostly absent, not completely, but there were very few observations of sunspots. So the dynamo seemed to have some switch between an active and a less active state. We know that the sun had kind of this sort of activity pattern for something like the past 100,000 years. And that is mostly what we get from tree ring data and ice core records of C14 and beryllium-10, which is essentially caused by, in the Earth's atmosphere, by the impact of cosmic radiation, which itself is modulated by the strength of the solar magnetic field. We do not have any longer records for the solar magnetic field. But of course, we have observations of other stars, and through that we know that stars have magnetic fields on much longer timescales than this. If you go even to larger scales, also galaxies have magnetic fields, and this is an example from M51. The two galaxies which interact with each other. If you have binoculars, you can actually see this galaxy with binoculars. It's near the Great Dipper. I can show you exactly where you can find it if you're interested. The magnetic field here is derived from polarization of radio emission, and people find typically micro-Gauss field strengths, and the magnetic field clearly shows the structure of spiral arms, right? You kind of see here that the direction of the magnetic field and the strength is kind of following the structure of the galaxy. But it's kind of interesting about galaxies, it's the only dynamo really in the universe which is optically thin. In principle, you can see through the entire region. In the sun, the biggest challenge with understanding the solar dynamo is that we can only see the outer boundary, the photosphere. We really barely have any information about magnetic fields inside the convection zone. I mean, I think these short bars here, they kind of indicate the direction. So, yeah. Okay, so to summarize, in the universe, we have objects from the size of a planet to galaxies or even larger scale galaxy clusters, which do have magnetic fields on the scale of the object itself. But the physical properties in these objects are vastly different, right? We're talking from scales of 1,000 kilometers or so in the case of the Earth to 100,000 of light years. In Earth-like planets, we talk about liquid iron, but in other stars and galaxies, we are talking about partially ionized plasma. We have spherical objects, we have disc-shaped objects. All of these objects have rotation, and the influence of rotation varies vastly. For example, the Earth is very strongly rotational constrained objects. The sun is kind of so at the boundary where where it transitions from weak to strong influence of rotation. But all of them are rotating. That turns out to be a very critical part, as I will show later. Another critical dimensionless number here, the magnetic Reynolds number, changes vastly. It's something like on the order of 1,000, a little bit less than 1,000 for the Earth, but if you go to galaxies and so, it can be 10 to the 18. The big question I really want to address here, is there a common origin to all these magnetic fields, and can we understand this on the basis of MHD? And you did have a lecture about the MHD equation, so I go only very quickly through this. Right? The MHD equation is basically validity of continuum approximation. If you have strong collisional coupling, which is not a requirement for MHD, but it makes life easy because you can just do single fluid approximations and have a scalar gas pressure. And you have non-relativistic motions, which is good enough for most of the objects we are dealing with. Of course, if you want to understand how magnetic fields are generated in accretion disks close to black holes, you have to go a little bit beyond this. And the MHD equation is a combination of fluid description through the Navier-Stokes equation with the non-relativistic Maxwell equation as well as Ohm's law. Now, in general, solving the full 3D MHD equations, while that becomes more and more possible with more powerful computers, it's still very challenging, and I'll talk to you about this in the second lecture. So just to understand on a very fundamental level, what ingredients do you need to make a dynamo, I will follow in this lecture kind of semi-analytical approach for just understanding how a velocity field leads to induction effects. And this is called the kinematic approach because you ignore the Navier-Stokes equation. You just assume we have a given velocity field. And what properties does this velocity field have to have that we actually can have a dynamo operating? So in some sense, the velocity field is assumed to be given as a background turbulence. The Lorentz force feedback is neglected. And so in order to do this, what we have to look at is just the induction equation. So a very brief reminder where this comes from. The one equation, this is based on this Ohm's law, which is following from the equation of motion for electrons, here formulated in terms of the drift velocity between electrons and the ions in the plasma. So you have here the electron acceleration term, you have a collisional term with collisions between electrons and ions. Then you have here the electromagnetic force on the ions, and you have the electron pressure. You can reformulate this equation in terms of the electric current, which give you Ohm's law. And I just highlighted here two terms in red. This is the most simplistic form of Ohm's law, where you just have a relation between the current and the electric field. And of course, the coefficient here is the plasma conductivity. And for the most of this lecture, we only use an Ohm's law of this very simple form. But I also would like to highlight this additional term here, which depends on the electron pressure. I come back to this one a little bit later. And then, so we have the simplified Ohm's law. And this is, of course, in the co-moving frame of the plasma. If you then have it in the rest frame, laboratory rest frame, you have to add in here the additional V cross B field, which just comes from the Lorentz transformation of the electromagnetic field. And then you put this expression for the electric field, right? I replaced now the current here with curl B. You put this into the induction equation, the BDT is minus the curl of E, and that way you end up with the induction equation for the electric magnetic field. And the eta here, which is the inverse of the plasma conductivity, is the magnetic diffusivity. So most of this lecture will just analyze this equation. You have to, for the most part, can forget about the rest of the MHD equations. Typically, this equation can be made dimensionless, and then you end up with a parameter in front of the dissipative term here, which is the inverse of the magnetic Reynolds number. And the Reynolds number essentially measures the amplitude of induction effects here from the V cross B term to diffusive effects coming from this curl B term. So it's a typical length scale times the typical flow velocity divided by the magnetic diffusivity. If we have a very low magnetic Reynolds number, this is a diffusion-dominated regime, and the induction equation just gets reduced to a diffusion equation. And it has only decaying solutions with a diffusive time scale, which is something like the typical length scale of the magnetic field squared divided by the magnetic diffusivity. And I show here what are typical time scales. So for the Earth, the outer core, the diffusivity is something like 2 meters squared per second. That is the diffusivity of liquid iron. Length scale is about 1,000 kilometers. Velocity is about 1 millimeter per second. You end up with a magnetic Reynolds number of about 300. So induction effects certainly dominate over diffusion, but not by a very large amount. Diffusive timescales are about 10,000 years. For the sun, if you do the same for just the plasma conductivity, kind of the Spitzer conductivities you get in the absence of any turbulence, you end up with a substantially higher Reynolds number, somewhere here about 10 to the 10 or something like that, 10 to the 9. And the main reason this Reynolds number is so much larger for the sun is because the length scale and the flow velocities are much larger compared to the Earth. Actually, the value of the diffusivity is more or less the same. And now the sun, at least in the convection zone, the outer 1/3 of the sun has strong turbulence. So essentially the effective diffusivity is much higher. So then you actually end up again with a much more moderate Reynolds number if you take this into consideration. You can also do liquid sodium experiments in the lab. And on my last, in my second lecture, very much to the end, I just give one example of those. And they have been used to actually do experimental tests of the dynamo theory I present here. And in a lab, you typically have the biggest problem in the lab is that your length scale and flow velocities are very moderate. So it's a big challenge to get substantial Reynolds numbers, and liquid sodium is a pretty nasty thing to deal with. So you need a lot of liquid sodium and pump it with high speed through pipes or whatever containment you have. So these are pretty tricky experiments, but people have done them to kind of verify the dynamo theory I will be presenting here. Okay. Yeah, that's even more scary. Yeah. Yeah, so if you now consider the advection-dominated regime, you can expand these curl V cross B term, and you get essentially three components here. You get an advection term, you get this field line stretching term, which is essentially the velocity shear in the direction of the magnetic field, and you have these compression term if you have converging flows, like, for example, a star is forming, right? You have a collapsing cloud. This term essentially would, in that case, tell you that the magnetic field gets amplified by that. You can write these much more compact in the form that the total time derivative of the magnetic field, which is just the combination of these two terms here in the front, is just given by this field line stretching term. If you actually have a compressible fluid, you can find a very similar equation. And in that case, the divergence of V you just replace with the equation of continuity, and then you can get a very similar form by just looking at the quantity B over rho. And for example, this equation very easily can tell you, for example, if you have vertical transport of magnetic field in a stratified medium, if you have no expansion in the direction of a magnetic field, so the right-hand side is 0, then magnetic field just scales proportional to rho. So if you take something from the base of the convection zone, bring it up to the photosphere of the sun, you have a density contrast of 10 to the 6. You would weaken the field by that factor of 10 to the 6. But if you do have expansion, at least partial expansion of these plasma along the magnetic field, which you always do, then the dependence on the density is less severe. And in the most extreme case, if all the plasma is just expanding along the magnetic field, then the magnetic field strength actually would not be changing at all. One way to think about this induction equation, which kind of leads to a very intuitive understanding on how actually the flow fields interact with magnetic field, is Arfvén's theorem. If you consider the flux through a kind of through a surface, which has the property that the boundary of the surface is moving with the plasma, then the flux through the surface is conserved. So for example, if you have an example, you have kind of a confined magnetic flux bundle here, and you have a shear flow, then this central surface here is displaced more strongly by the shear flow than the other ones. So the action of the shear flow will be just that it bends the field line like this and stretches them out. That's a very intuitive way to understand how flows and field interact. And people very often describe this as that flux is frozen into the fluid or field lines move with the plasma. Okay, so this is just a little bit background about induction equation and so on. So let's move on to dynamos. So for zero velocity, all magnetic field has to decay on a time scale of this diffusion time scale, which is typically rather short for most objects we are dealing with. But we do have evidence that many objects in the universe have magnetic field sustained for much longer time scales. And most importantly, the magnetic fields seem to be very dynamic. They evolve on time scales, which are very often even much shorter than the diffusion time scale. So this leads to the idea that there must be some active process happening maintaining this field. So this is a very abstract definition of what we're actually looking at. So essentially, you want to look at a situation where you have a magnetic field which is maintained by currents which only flow within a very confined volume, which is here just called S, which could be, for example, the star itself. Inside this volume, you want to look for a solution of the induction equation, and then outside the volume, you have a potential field, and you smoothly couple the field across the boundary to this potential field. The velocity field is zero outside, and inside this volume, you do have arbitrary fluid motions, which do have a finite kinetic energy. And then you call this a dynamo if essentially this B equals zero solution, which is always a varied solution for the induction equation, is unstable, meaning if you just put in a very weak magnetic field, you get an exponential growth of the magnetic energy inside this volume. This is very abstract, so let's just think about it a little bit, what it means. You're likely very aware with dynamos and power plants and so on. So what do you think is similar and different between this dynamo and the dynamo and power plants? I mean, normally when you do electrical engineering, you normally don't solve this equation at all. Do you know what the reason for that is? I mean, what is the most important building blocks of dynamos and power plants, which you don't have in stars? I mean, you do have motions in both, and of course, you don't have a liquid material in a power plant, but actually you do have motions, and most importantly, right, the most important induction effect comes from shear flows, where in the direction of the magnetic field you have some variation of the motions, and all power plant dynamos, they at least have a rotating part and the stationary parts. In that sense, you actually have these shearing motions. You do have differential rotation in some sense in there. But what is the other big difference? Certainly, that is a very big difference, yes. But how do you build a dynamo in a power plant? What is the most important building block? Electric wires, right? Stars don't have wires. But in some sense, that difference looks large, but it's not really. What it just means is in a power plant, right, these eta here, which is for simplicity in stars just a constant, so currents can just flow anywhere you want. Essentially, you have a short circuit all the time. In a power plant, this eta is highly inhomogeneous, right? You only allow the currents to flow in certain locations. That is the main difference. So in some sense, the main difference really is this, that you're inhomogeneous versus homogeneous dynamo. In a power plant, a short circuit is a major disaster. You absolutely don't want this. But in these astrophysical dynamos in stars, you have a short circuit all the time. The question is, can you even in that situation maintain still magnetic fields? And of course, in power plants, since you control the currents, it's mathematically much more easy to formulate the mathematical description of these dynamos in form of currents. That's the reason when you do electrical engineering, you will not solve the induction equation, you deal with the currents directly. But if you go to astrophysical dynamos where you have no control over the current, it's mathematically much more convenient to just deal with the magnetic fields and just have the current as a derived quantity. Once you have B, you know what the currents are by just computing the curl of B. Okay. One other aspect of these dynamos, you can compose the magnetic field in small scale and large scale components and kind of split up the energy into the energy of the large scale field and the small scale field. And you remember like the magnetogram of the sun I showed you, they have some large scale field components like the sunspots. And you have these very small scale feed components which look like a salt and pepper pattern everywhere. So there is a distinction of dynamos based on where most of the magnetic energy is. If you have basically no large scale field, no magnetic field on the scale of the system, you only have these small scale field, you call it a small scale dynamo. But if you have at least a substantial amount of energy in the large scale field, it typically does not become much larger than a small scale field because you can only maintain these large scale field by also having small scale field, and I come back to this later. Then you call it a large scale dynamo. It turns out that almost all turbulent chaotic velocity fields have this small scale dynamo property. But if you want to have a large scale dynamo, you need additional symmetries in the system. So what does large scale, small scale mean? Large scale is pretty much anything which is aware of the larger scale in the system. So if you look, for example, in this magnetogram on the sunspots, right? They have these preferred symmetries. They certainly know on which hemisphere of the sun they are. They are part of the large scale field. But then if you look somewhere away from sunspots into these salt and pepper pattern, and this is a more detailed field of view from a Hinode magnetogram. This is kind of a scale, something like 100 times 200 megameters. So it's kind of like a small box, something like this here. You kind of see the salt and pepper field on very small scales. And if you just randomly choose a box like this in the northern hemisphere and the southern hemisphere, you couldn't really tell it apart. So this is really a component of the field which doesn't really care about any large scale properties of the system. That would be definitely the small scale component. But there is a smooth transition between the two. You cannot really draw a very clear line. What is large scale, what is small scale? Because, for example, if you're looking close to sunspots, some of the sunspot field decays. And then you see more, for example, of the negative polarity near this spot. You see a little bit more of the positive polarity outside this spot. In that case, you have some mix here. You have some small scale field, but you also have some of the larger scale field mixing in with it. So it's a smooth transition. You cannot just draw a very clear line between the two. Let's first talk about the small scale dynamo action. And I want to motivate it here by just getting a very rough idea what it is about. Let's assume you have a velocity field V, and you just put in two Lagrangian particles which just follow the velocity field at a position x1 and x2. And then you consider the separation between these two particles, and you derive an equation. You just take the difference between these two equations, and then since this delta is assumed to be very small, you can do kind of a Taylor series expansion of the velocity field. Then you get this equation, which tells you how the separation of the particles evolve with time. And essentially, when this equation has exponentially growing solutions, this is essentially then a chaotic flow. It has a positive Lyapunov exponent, at least in one direction. That is essentially the definition of what one calls a chaotic flow. And turbulent flows have this property. Now, just by looking at the induction equation, you actually see that this form of the induction equation we derived earlier has exactly the same mathematical form, which essentially means is if you have a chaotic flow and you sprinkle in a weak magnetic field, that magnetic field has to grow exponentially as well, just because these two equations are mathematically the same. Now, of course, the induction equation also has some diffusive term here, which will prevent this exponential growth. So typically what happens is you only find this exponential growth if the magnetic Reynolds number is large enough, typically something on the order of 100. And this is essentially the essence of a small scale dynamo. Any turbulent chaotic flow has this property. At a high enough Reynolds number, you will see exponentially growing solutions. But life is very often a little bit more complicated. And over the last 10, 20 years, when people studied these dynamos, there was some concern regarding the role of the magnetic Prandtl number. The magnetic Prandtl number is the ratio of the magnetic Reynolds number over the fluid Reynolds number, or its ratio of viscosity to magnetic diffusivity. And essentially what it tells you is, where does this small-scale dynamo actually operate relative to the turbulent velocity spectrum? So the blue line here indicates the kinetic energy power spectrum. If you have a large magnetic Prandtl number, the small-scale dynamo, at least in the kinematic growth phase, when the field is very weak, most of the energy, most of the induction really happens here in the dissipation range of the velocity field, where the velocity field is very smooth and it doesn't really have flow scales on scales smaller than the magnetic field. And this, people studied these high magnetic Prandtl number dynamos first because it's most easy to do this in numerical simulations. But the problem is that stars, for example, the sun has magnetic Prandtl number of about 10 to the minus 5. So you actually have to make this dynamo work inside the inertia range. And what this means, you have certainly these large-scale shear flows, which are very efficient in inducting the field, but you also have a lot of very small-scale turbulence, which is much more efficient in adding a turbulent diffusivity, which again destroys the field. So there was a concern that this could lead actually to a situation where the dynamo is much more difficult to excite. And when people studied the Prandtl number dependence early on in simulations, when they started coming from the high Prandtl number to the low Prandtl number regime, what they found is that actually the critical Reynolds number you need to exceed is increasing as you approach lower and lower Prandtl numbers. And for a long time, it wasn't clear if this just continues to go up or if it will turn over at some point. And only actually a year ago, people were finally able to do these kinematic dynamos at a very high, at a very low magnetic Prandtl number, something here, a few times 10 to the minus 3. They actually found is that eventually this turns over again and these small-scale dynamos become more easily excited. So right now, it looks like this issue has been resolved, that even for the low Prandtl numbers like 10 to the minus 5 in the solar convection zone, it's still possible to keep the small-scale dynamo operating. And I will talk more about small-scale dynamos in the second lecture today. I want to just show here a very rough sketch how you actually make a dynamo work. I mean, in a very simplistic way, just think of a magnetic field line as a rubber band. How do you kind of stretch this and twist it up to actually have a cyclic process where you can induce more and more magnetic field? So we start with one magnetic field line here. We stretch it out. We twist it one time to a figure 8. And then we kind of fold this back on each other. And then we end up now with these two magnetic loops, but not quite, because you have this crossover point here. If you then have some reconnection here at this crossover point, in the end, you end up with two loops. So you essentially, right, by stretching it, you double the field strength. And then you have now two loops. So you also have twice the magnetic flux, and then you can continue this process over and over again. A different way to do this is you can again stretch this out. Then you bring these field lines together here in the center, you reconnect here, then you end up with two loops, and then you just shift them on top of each other. So you end up in the same process. The one important thing I want to point out here are two things. Actually, the one is any of these two processes you can only do in 3D. You cannot make this work in 2D, and that is a general property. I mean, pretty much all these dynamos, they require 3D. There might be some very exotic cases if you have some crazy anisotropic magnetic diffusivities where you can make something work under different conditions. But if you just have ordinary magnetic diffusivity, you need a 3D space to make this happen. The other thing is you need, yeah? There are no things, there are no field lines. There are no things in 2D, right? In 3D. What do you mean in 3D? Only works in 3D. Yeah, I mean, in some, right, you have to kind of bring this, right? For example, the twisting you have to do, you need 3D, and then you have to kind of fold this up where you have to go to 3D. In this case, you kind of have to repacks this by kind of shifting the two loops on top of each other. I mean, yeah, I mean, you can have this embedded in a 3D space. I mean, you can have much more complicated structures, but you can just have a magnetic flux tube kind of, right? A toroidal magnetic field loop close into each other. This is just an illustration to just highlight some very basic properties, but the field in reality can be much more complicated than that. One important thing I wanted to point out is you need somewhere in this process, either here or here, some magnetic reconnection to actually complete the process. But there is a very fundamental difference between these two ways to do it. Right? If you take a rubber band and do this, and you do not reconnect the rubber band, you actually can continue this multiple times without ever having to reconnect the rubber band. It just, you induce some very small scale twist on the rubber band, which just builds up and makes it much more complicated, but you can continue this process. Whereas the second process here, you have to explicitly cut your rubber band and reconnect it. So if you now consider the situation that you reduce the magnetic diffusivity, set towards 0, this process here will become very slow and inefficient, whereas this one you can continue because these topological features you have to reconnect away, they will kind of propagate to smaller and smaller scales. And that leads to another distinction of dynamos. Essentially, a fast dynamo is where the growth rate is independent of the magnetic Reynolds number, whereas a slow dynamo, the growth rate will be limited by resistivity because you have this explicit resistive step in there where you have resistivity on a large scale having to reconnect the field. When we talk about astrophysical systems, you're always interested in fast dynamos because all astrophysical objects have these extremely large Reynolds number. A slow dynamo wouldn't work in the astrophysical context. Okay. Now look at a very basic example. Let's consider a star like the sun. And let's just look at the axisymmetric situation. So we have an axisymmetric magnetic field, which you can write in this way that you have the toroidal field, which is in the azimuthal direction, and the poloidal field, which you can express through a scalar vector potential. And you can do the same for the velocity field. And the velocity field, we have a meridional flow, which is our theta components in the differential rotation in the azimuthal direction. And we do know for the sun, for example, what the differential rotation looks like, and the meridional flow for the most part, what we know for sure is that it's poleward near the surface. There's some debate on what it looks like deeper in the convection zone. But if you now look at this most basic example and you put this into the induction equation, you get these two equations for the toroidal field B and for the vector potential of the poloidal field. And for the most part, the meridional flow component is just transporting these fields around within a meridional plane, within the r theta plane, but it doesn't really do anything dynamo-wise in actually amplifying the field. So we can for now ignore these terms. Then you have the red terms here, which are just the magnetic diffusivity terms, which lead to a decay of the magnetic field. And you have the differential rotation term here, which actually takes the poloidal field, which you get from the curl of the vector potential here. And this becomes a source term for the toroidal field. So when you, for example, start with a very weak poloidal field, so only have an A in here, and you have a very strong differential rotation, you can have a situation where at least initially you see a strong increase of magnetic energy because this term will build up a strong toroidal field. But this initial strong increase in energy does not mean you have a dynamo, because eventually, since there is no term here which can maintain the magnetic field in this equation, the poloidal field will decay away. At that point, this term vanishes, and also the toroidal field will decay away at this point. So that's one important thing is when you want to evaluate if a certain flow field is a dynamo, you really have to run it for long enough. And long enough means multiple ohmic decay timescales before you can be sure if it's a dynamo or not. So obviously what is missing here is we need an additional term which can regenerate the poloidal field from a toroidal field to actually make this a dynamo. But this is actually a little bit hard because the problem we are seeing here can be actually proven much more formally. There are a lot of anti-dynamo theorems, and Cowling's anti-dynamo theorem essentially says that if you have a stationary exomagnetic field with currents limited to a finite volume in space, you cannot maintain this field by having a velocity of finite amplitude. So it's kind of a big no-go. The only way you can actually make this work, you need a much more complex field. You have to add a non-axisymmetric magnetic field components. And just a very brief history, how dynamo theory came along. In 1919, there were the first suggestions that magnetic fields, the solar magnetic field may be maintained by motions of a conducting fluid. But when people really got serious about studying this, the first things they found is essentially all these situations where it cannot work. And really the idea which got this going was 1995 by Gene Parker, and he suggested do a decomposition of the field into axis and non-axis symmetric parts, and then average over the induction effects from these non-axisymmetric fields to actually get additional induction effects which can maintain the axisymmetric field. And this was then later more formalized here by Braginski, Steenbeck, and Krause in form of the mean field theory, which I would like to introduce in the remaining slides in this talk. And only in the last 2 decades, we had essentially 3D dynamo simulations. Yeah. Yeah, okay, yeah. So in order to do this decomposition in mean field and fluctuating parts, you have to do some averaging of differential equations. And in order to actually do this, you want to only consider averages which follow these set of Reynolds rules, mostly because when you have derivatives, you want to be able to kind of exchange the averaging procedure, that the average of a derivative is the same as the derivative of the average quantity and so on. That is just to be able to manipulate the differential equations. So for example, if you have the axisymmetric mean, like the longitudinal average, that fulfills these Reynolds rules. Another average you could consider is an ensemble average, right? You have a turbulent system, you average over a large amount of realizations of these turbulent systems to define your mean. If you apply these averaging to your induction equation, you can derive an induction equation for the average field, which looks pretty much the same, right? At least as far as these terms considered, but you do get this term, which is the average of the fluctuating parts of the velocity field and the mean field. And this is a new term in the induction equation, and which is called the turbulent electromotive force. And this is essentially the essence of mean field theory, to kind of study under which conditions these additional terms you get in here can actually enable a dynamo which maintains the large-scale magnetic field. So in principle, how you go about this is you also, when you subtract this equation from the induction equation, you can derive an induction equation for the fluctuating parts. And if you have a mean field, you essentially have this term here, which is the generator of your fluctuating magnetic field. You essentially want to solve this equation for a given mean field to evaluate what the fluctuating field is. And once you have that, you can compute the electromotive force, and then you can evaluate whether this electromotive force actually is maintaining your mean field. The problem is solving this equation is way more complicated than it might look like, but it's a not easy task to do. So in general, just to study kind of general properties, people do a strong simplification, essentially that they expand these electromotive force in terms of components of the mean field and the first order derivatives of the mean field. And the assumption which really goes in here, that you do have a strong scale separation, meaning that the scales of these fluctuating fields are much larger than the large scale which defines your mean field, and also the correlation time of the turbulence, it's much shorter than the large scale, the evolution of the system on the large scales. So the question is now, if you have an expansion of this form, what are the properties of these coefficients A and B you need to be able to enable actually a large scale dynamo? It makes sense to do a little bit mathematical nudging of these coefficients to write it in an equivalent form. Essentially, you separate these A coefficients in a symmetric and anti-symmetric part, which gives you these first two terms. And then you decompose this gradient tensor of magnetic field in the curl of B and some other terms, which I ignore here to keep things simple. And then you again do the same trick, that you decompose this tensor you have in front of the curl B into the symmetric part and the anti-symmetric part, which gives you these coefficients or tensors alpha, gamma, beta, delta. And there's nothing new I put in here, it's just a rearrangement of terms. And if you put this now back into the induction equation, you see that some of these terms look similar to terms you already had. For example, this gamma term looks like a velocity, whereas this beta term looks like the magnetic diffusivity. So if you had already trouble getting a dynamo to work with these gamma and with the velocity field and the eta term before, it likely won't help you here. Now there's one exception, of course. This beta is now a tensor, and it can be very complicated. It can be anisotropic. It could be even not positive definite. So there are some very exotic situations where this one could produce a dynamo action. But the most interesting term is actually this alpha term, where you induce a magnetic field, or you have here a term which is just proportional to the toroidal field. And that gets back to what I showed when I did this decomposition into the axis and non-axisymmetric part. We needed this term to maintain the poloidal field for a given toroidal field. And as I will show later, this alpha term will actually provide that. You can do some analysis of symmetry constraints, but for the sake of staying on time, I will skip over this, but just give you the summary of it. Depending on what sort of turbulence you have, if you just have isotropic turbulence, for example, you only get this beta term, which is something like an enhancement of diffusivity. That is called turbulent diffusivity. If you then add stratification to the problem, you have again this beta term, but it becomes anisotropic with the direction of stratification. In that case, you can get this gamma term, which is a transport term, which acts like a velocity. And if you have only rotation in the system, but no stratification, again, you can have this beta term, but it now has some anisotropy with respect to the rotation. You can get this additional delta term, right, which is this one here, which can be actually a very exotic, lead to some very exotic dynamo effects as well. But this alpha term, which is actually the most interesting for dynamo action, only exists if you add stratification and rotation together. And you can actually derive what these alpha, gamma, and beta terms should be if you make some strongly simplifying assumptions, like the fluctuating field is very weak compared to the mean field, and you have quasi-isotropic turbulence, but it is non-mirror symmetric, so you can have helical flows in this turbulence. And if you do this, you actually can derive very simple terms for these expressions. And what you actually see is that this alpha term in this particular case will be a scalar, which is proportional to the kinetic helicity of the flow, to the negative kinetic helicity. The beta term, which I call here now the turbulent diffusivity, is just given by the convective flow amplitude squared times the correlation timescale is 1/3. And this gamma term, which is a transport term like a velocity, sees actually the gradients of the turbulent intensity. And so if, for example, if this correlation timescale is invariant of space, you can just write this as the gradient of the turbulent diffusivity. And so let's first think about this first term, the turbulent diffusivity. This one just is a term which enhances the dissipation of magnetic fields. You can write this expression essentially, it's on the order of something like a length scale times the turbulent RMS velocity, because if you take the correlation time scale times the velocity, that roughly gives you something like the length scale of your turbulent eddies. And this one you can now write as something like the magnetic Reynolds number, like the microscopic diffusivity. So this is a dramatic enhancement of the effective diffusivity of the plasma. In the case of the sun, magnetic Reynolds number can be something like 10 to the 10. So this is a very dramatic effect. And yeah, let's leave it here. So this gamma term, it's sometimes also called turbulent diamagnetism, mostly because it has a transport velocity which sees a negative gradient of turbulent diffusivity. So essentially, when you have turbulent diffusivity which varies in spaces, what this term is, it expels magnetic field from regions of strong turbulence. Another way to think about this is also turbulent pumping. In the convection zone of the sun, you have the fastest flow velocities near the photosphere of the sun. So this gradient, right, with a negative sign leads to a gamma term, which is radially inward directed. So that's the reason why people call this turbulent pumping. If you put a horizontal magnetic field somewhere close to the photosphere, this effect describes the transport of magnetic field into the solar interior, downward transport. And now this alpha term is now the most interesting one related to the kinetic helicity. So what this term is doing really is the following. In order to get this, you need both rotation and stratification at the same time. If you have stratification, what it means is that upflows have to expand and downflows, they have to contract. At the same time, since you have rotation, you do have Coriolis force acting on these flows. So in this case, the expanding upflows, they will turn clockwise, whereas the contracting downflows, they turn counterclockwise. But that means in both cases, it follows kind of the left-hand rule here. You have a negative helicity in there, which means in this case, you would get a positive alpha effect. And what this alpha effect is really doing, if you have now a horizontal magnetic field line threading through here, is that you first, by the upflows and downflows, you bend this magnetic field line, but at the same time, you twist it. And then when you twist these loops you bend up here, essentially what you do is you add again a poloidal field to this toroidal field you started with. And that is the essence of the alpha effect, and that is the reason why it actually makes a dynamo work. So you can look at this by first inspecting the induction equation for the mean field. So you have a sink for the mean field, which is the ohmic dissipation of the mean field. And then you have here a thing which is related to Lorentz force work the mean field might do. But the other term here, when this new electromotive force comes in here, you have this J dot E term, which is actually the induction by energy conversion by the alpha effect. And you see here that the alpha effect can actually pump energy in the mean field if you do have, if this J dot B isn't zero, which is also called the current helicity of the magnetic field. Now, a different way to look at this is just the following. You put this alpha B in your induction equation, and you get now an equation of the form that the induction effects are this way, that you induce a new mean field, which is proportional to the mean current. So for example, if you do have, let's start, you have a poloidal magnetic field. the mean current you're having is actually a toroidal current. And this equation now tells you if you have an alpha effect present that you actually induce a toroidal magnetic field B. The toroidal magnetic field B has no colloidal current. And so you, again, with this toroidal magnetic field, you induce a polloidal magnetic field. So this alpha effect kind of allows you to go constantly from a toroidal to a polloidal field back and forth. And that way you can go through a dynamo cycle and maintain the magnetic field. And at least from this very basic example, you can see that in general, you would expect stationary solutions. It can just maintain the magnetic field you have here in place. If you add no differential rotation to it, a large scale shear flow like we have it in the case of the solar convection zone, and let's assume we do have a toroidal magnetic field in here which points in the azimuthal direction of the sun, the alpha effect creates a polloidal current loop, but since you now have a shear flow, you shear this loop and you produce a new toroidal flux system. But this loop on one side, it adds to the magnetic field, the toroidal field you had here on the left side, but on the opposite side, it actually subtracts from it. So from this, you can actually see if you add these alpha effect together with a shear, you actually can get propagating magnetic activity patterns. And they are called a dynamo wave, even though it's formally, if you look at the equation, it's not really a wave equation, but it's a traveling activity pattern. And this activity pattern actually would propagate along the contours of constant angular velocity. And this is essentially called the Parker-Yoshimura rule based on Parker and Yoshimura, who first discovered this. So if we go back to this set of equations which describe the evolution of an exomagnetic field now, if you put in the alpha effect, right, then we have now here a closed system. We have now a term which can regenerate the polloidal field from a toroidal field, and you can vice versa with the omega effect maintain the mean magnetic field. And that way you can circumvent this problem we had earlier in maintaining a large-scale magnetic field, which is axisymmetric. So the large-scale magnetic field can be still axisymmetric, but we have no small-scale magnetic field, which is non-axisymmetric, we did average over. That is why this actually works. Let's skip over this. Let's see how much more time, yeah. So one interesting aspect of these dynamos is that they tend to produce helical magnetic fields. The magnetic helicity is defined as the product between the magnetic field and the vector potential. And the reason it's an interesting quantity is that it follows a conservation law. Now, if you integrate, I mean, if you put in the induction equation, compute the time derivative of the helicity, assume you have a bounded volume and you have no helicity fluxes over the system, what you find is that the time derivative of the helicity is given here by this dissipation term, which has here the magnetic diffusivity and the current helicity. This is if you just take the standard induction equation to derive this. Now, if you put in these, if you do this now for the mean field induction equation, you get very similar expressions, but you do get this additional term, which depends on the mean field electromotive force. So if you have a dynamo operating and the mean field electromotive force has a component in the direction of the mean field, you essentially produce a helicity separation. You induce helical magnetic field of one sign on the large scales and helical field of opposite sign on the small scales. So you need to get a separation of helicity. The total helicity, if you add the large scale and small scale together, this term drops out. And you can use this in the asymptotic expression, for example, to estimate the helicity of the small scale field here, which is negative, has the opposite sign of the alpha effect itself. And then you have also some additional term here, which comes from the turbulent diffusivity on it. And I will come back to this expression just in a minute. But before that, I would quickly, since we only talked about kinematic effects, talk about non-kinematic effects, how does a dynamo like this actually saturate? Now, the proper way to do this would be doing 3D simulations, so you have the Lorentz force feedback in there, and I will show some examples of this in the second lecture. But that's in general still very difficult. But so how could you get at least some understanding how these dynamos saturate? So you can actually do mean field models, which you expand a little bit, where you, in addition to the mean field induction equation, you also solve some mean field equation for the large scale flows like differential rotation and the Marionne flow. And from the mean magnetic field, you can compute the Lorentz force, and at least this green component here, which is the large scale part of the Lorentz force resulting from the mean fields themselves, you can in principle plug this back and for that have a feedback of the Lorentz force on the mean flows. For example, you can have a situation where these, right, if you have an alpha omega dynamo like in the sun where you have a strong shear from differential rotation, you would get a Lorentz force which actually tries to limit the shear of differential rotation and then reduce the amount of differential rotation, and through that can actually saturate the dynamo. And this I would consider here the macroscopic feedback, but you can also have feedback on smaller scales, like you can change these turbulent induction effects like the alpha effect. And when people do mean field modeling, very often they use an expression of this form where this kinetic alpha effect is reduced once the magnetic field has a strength comparable to the equipartition field strength. And equipartition field strength is the strength at which the energy density of the magnetic field is comparable to the kinetic energy density of the magnetic field. And this is an expression which is used quite often because it kind of does a job. But the problem with this expression is if you actually do the math, it turns out to be a little bit more complicated. And for that, I have to come back one more time to helicity. And I just want to introduce this concept here through a very easy symmetry argument. So I wrote down here very simplified induction equation. I only use this stretching term here. The momentum equation has a very similar term in here. This comes from the Lorentz force. And you kind of see that these equations have an interesting symmetry. If you formally replace the velocity with the magnetic field and vice versa, these equations are actually just stay the same. They just turn into each other. At the same time, we have the electromotive force, which is V prime cross B prime. Obviously, if you formally replace V with B and vice versa, this term has to actually change the sign. So far, we only considered this contribution in the alpha effect, but this is obviously not consistent with the symmetry in the equations. There is a term missing, which depends on the magnetic field. And in order to make this actually consistent with the symmetry, you need in the alpha effect an additional magnetic contribution, which depends on this small scale current helicity. And that now I come back to this term I earlier derived, that you can estimate that an alpha effect introduces a small scale current helicity. And then you can add this term here into this alpha effect term, which is the same as I showed before, the alpha k. This is just the kinematic component coming from the velocity alone. If you do this now, you actually see that you expect to get an alpha quenching term of this kind. The only difference is that you have here the ratio of the turbulent diffusivity to the magnetic diffusivity, which is a magnetic Reynolds number. And that is a big concern, because that means you have something which people call catastrophic quenching of the alpha effect, where already for magnetic fields much weaker than the equipartition value, this alpha effect would disappear, since the magnetic Reynolds number is very large. Now, this only happens when you consider a situation where the large-scale field is just a homogeneous B field. But if the large-scale field itself is maintained by a dynamo, it's helical itself, and then you have some of these additional terms in here. If I go back, right, you have these additional terms which do not necessarily vanish in this very catastrophic way. You also could have helicity loss, and one idea is how to actually prevent these catastrophic quenching is that the dynamo has to constantly shed small-scale helicity through the boundaries of the system, and the sun is obviously doing it. That is all the coronal mass ejections you see all the time happening. And if you estimate the helicity loss for all the mass ejections, at least it roughly adds up to a value where you could get a dynamo continue to work with the alpha effect. But I just wanted to highlight here that really how these dynamos saturate can be in detail a very complicated process. And this is still not a completely settled question. This comes up again and again. And what really makes it hard is you cannot simply do a 3D simulation and figure out how you get around this, because in 3D simulations, very often your magnetic Reynolds numbers are not high enough that this really becomes a problem. So we have a lot of 3D simulations which work fine, but that is maybe because they don't have these problems with catastrophic quenching, but they would be if you could do a 3D simulation at the magnetic Reynolds numbers of 10 to the 10, which we actually can't do. I will talk about 3D simulations in the second lecture, so let's just skip over this. One last thing I would like to ask you the question, where actually did the first magnetic field come from? Because if you have an induction equation of this form, B equals 0 is always a solution. So how do you actually get a magnetic field in the first place? And when I introduced Ohm's law earlier today, I had this additional term in there, the electron pressure gradient. If you remember, this was highlighted in green. So if you keep this term actually in here, in the equation for the relation between J and E, you actually get an induction equation of the form where you have this additional term in here, which is a source term for magnetic field, which doesn't depend on magnetic field itself. And with that, actually, you can create magnetic field from scratch. And for example, some thoughts where the first magnetic fields came from is when you had kind of the early universe, you had ionization fronts from kind of the first bright objects in the universe, either stars or even on scales of galaxies, which essentially were driving ionization fronts through an inhomogeneous medium. And that essentially led to a situation where these gradient of the electron density and electron pressure were not zero. In that case, you would estimate it's a weak field of 10 to the minus 23 Gauss you can produce. Then you have collapse of this to form galaxies, which amplifies it a little bit. Then you can have a galactic dynamo working on it. So in principle, over the 10 gigayears or so, you could get to the 10 to the minus 6 Gauss of galactic dynamo have today. And then this magnetic field kind of collapses, and that becomes the seed field for stars. But even if you forget about all of this and do a very extreme Gedanken experiment, just go to the sun and set the magnetic field to 0. How long does it take for the sun to remagnetize? Now, the interesting thing is that this term, you can also compute this term in the photosphere of the sun, and you will see that this is in particular strong at the edge of solar granules. And that was estimated by the paper by Elena Komenko a couple years ago. You get actually a field on the order of 10 to the minus 6 Gauss. Then you have this very efficient small-scale dynamo that has a growth rate likely on the order of minutes. So if you set the magnetic field to 0 on the sun, you start with 10 to the minus 6 Gauss immediately with this dynamo growth rate of a few minutes. You just have to wait a few hours, and all this salt and pepper field in the quiet sun is back to where it is today. Now, to get the magnetic field organized on larger scales, you have to wait longer. If you want to get the field organized on a scale of supergranulation, which has an overturning time scale of a day or two, you have to wait a day or two. If you want to get it organized on the scale of the convection zone, you have to wait for overturning time scale of the convection zone. But at least the small scale field will be back almost immediately. The large scale field, likely you have to wait something equivalent to several solar cycle timescales, several hundred years for that to come back. But all these timescales, they are extremely short to the life cycle of a star. So in some sense, it's completely unavoidable to have a magnetized star like the sun. Even you set it to 0, it will reset itself very, very quickly. Okay, that's pretty much it for this part of the lecture. So the next lecture, I will talk about a lot about the solar dynamo and then make some comparison of solar dynamo to dynamos in solar-like stars, and also talk a little bit about the geodynamo mostly by comparing what is actually similar and different. Okay, thank you very much. Okay, yeah. There is one.
I was wondering about what I think you were calling diamagnetism.
Yeah.
This, I was wondering about if the conclusion of that slide was that because the sun has a actually radial outward gradient in velocity, that means it's actually pushing fields it generates inward.
Yes.
That is happening.
Yes. That's called turbulent pumping. But that's only happening beneath the photosphere of the sun. Actually, once you go above the peak of velocities in the granulation layer, pretty much at optical depth unity, this term actually changes the sign and then it pushes field out. And some of that is actually seen in the sun. Mostly in the quiet sun, people found that if you go above the photosphere, you have a preference for horizontal field. And that might be part due to that term, that horizontal fields in the photosphere are actually pushed out. And the preferred location for that field to exist is in the velocity minimum, which is about 400 kilometers above the photosphere. So yeah, there's kind of, at the photosphere, you have a divergence in the transport by this term.
And the fields that are getting pushed inward, do you think that helps to sort of organize and grow a large-scale field?
Yes, it's certainly the case. I mean, one problem is for at least some mean field dynamo models people have been putting together for the sun is if you take the turbulent diffusivity for the magnetic field as you expected from mixing length theory, that's actually a pretty large value. And that would actually very efficiently transport the magnetic field towards the boundaries of the convection zone, which actually makes it sometimes very hard to make these dynamos work. So having strong turbulent pumping in the surface layers to keep the push the magnetic field in can be very helpful there.
Thank you.
I don't know much about dynamos. This could be a naive question, but if you sort of need the fluid to move around and create shear flows to generate field, does that mean that plasma beta is a useful sort of parameter to characterize whether a dynamo can exist or not?
In general, yes, because you really want to do a lot of work on the fluid. And that mostly happens in situations where really, right, the magnetic field is kind of weak compared to the gas pressure, so that really you have a lot of kinetic energy around which can act on the magnetic field and shear it up. When you go in a low beta region, it's typically the opposite way, that the magnetic field actually releases energy and does work on the fluid. Like in the solar corona, you would not necessarily expect to have a dynamo operating there.
How much do we know about when a dynamo action breaks down? Like, what could break down a dynamo?
You mean break down in terms of saturating, where it kind of kills off the kinematic growth, or really in the sense that it completely kills the dynamo?
Killing of the dynamo.
Well, I mean, one big concern, that's the reason why I actually added it in this lecture, is this catastrophic alpha quenching, right? Which I had in here related to the magnetic helicity. You have a buildup of small-scale helicity, which through this additional term in the alpha effect can actually completely offset the alpha effect. And this has been a big concern because, I mean, the magnetic Reynolds number in the sun is something like 10 to the 9, 10 to the 10. So essentially, it would mean that the alpha effect already should saturate when the feed of the dynamo is something only 10 to the minus 5 times the equipartition feed strength, which is extremely weak. So in that case, if we are really having a situation where you cannot find any way to circumvent this catastrophic quenching of the alpha effect, at least a dynamo using the alpha effect wouldn't work. Now, there are other effects. I mean, you remember maybe early on I had these additional delta effect, which I didn't discuss much. But there are some other effects you can maintain magnetic field which are non-helical, which would not be subject to this catastrophic quenching. So there are other things. But in general, it looks like from everything we know, at least when you have a high magnetic Reynolds number, it's close to impossible to avoid this dynamo action. At least the small scale magnetic dynamo, what we know right now is if the Reynolds number is larger than a few hundred, and you cannot avoid it from happening. And people were early on concerned about the influence of the magnetic Prandtl number on it, but at least the most recent research showed the magnetic Prandtl number, if you go to low Prandtl numbers, you raise a little bit the critical Reynolds number, but not that much that you would avoid the dynamo completely under the conditions you have in stars. So in general, I would say the only situation where you can be sure that you don't have a dynamo if your magnetic Reynolds number is too low, and too low means typically lower than a few hundred. Otherwise, it's unavoidable to have this happening.
I have a relatively basic question. Is the average 11-year periodicity of our solar cycle a function of the rotation rate of the sun? And do stars that rotate faster have shorter solar cycles or stellar activity cycles?
Yes, and I will talk a little bit about this in the second lecture, but in general, people see a trend that the cycle period gets shorter if you have a faster rotating stars. But as I will show in the second lecture, even for the sun, people don't necessarily 100% agree why we have an 11-year cycle. So it's kind of a challenge since we can't actually measure the magnetic field in the convection zone. We only see what boils up to the photosphere actually. Even though we are that close to the star, it's still a big mystery how it actually produces a large-scale field. So you made it through most of the equations. I think this part of the talk is mostly equation free. It's more figures and movies. So it's more about now actually applying this to understand the sun, stars, and planets. So just to start with talking a little bit about the solar magnetic field. I mean, I already mentioned in the previous talk that the large-scale solar magnetic field has certain symmetries, which are shown in this movie, which shows the evolution of the photospheric magnetic field over multiple cycles. And what you can see is that at any given time, the sunspot in a given hemispheres have a preferred polarity, where always the leading and trailing spot have the same polarity, but then in the southern hemisphere, it's the opposite. And every 11 years, that polarity again changes. Then you kind of see is that from the sunspot, you see some of these magnetic field actually being transported towards the poles, which then leads actually to the reversal of the polar fields. If you look at the sun in white light, you do see the sunspots mostly as these dark features, since the magnetic field is strong enough that it can locally suppress the convective energy transport. If you look at these sunspots in great detail, you see these marvelous fine structure of sunspots. You have the dark umbra, where convection is mostly absent, not completely, but mostly, but then you have this regime of transition called the penumbra and towards granulation further out. So if you want to have a large-scale dynamo theory, you want to explain how essentially at least the large-scale patterns come about, not necessarily all the detail of the sunspot structure. But if you look at large-scale flows, you also do see some solar cycle dependence of large-scale flows. This first panel here shows something which is called the torsional oscillations, and this is essentially showing the changes in the differential rotation over the solar cycle. And what you actually do see, you see these bands of faster rotating and slower rotating fluid, which kind of follow the butterfly diagram of the solar activity. You see the contour lines overlaid here indicate the butterfly diagram. Helioseismology can also look at these changes in differential rotation throughout the solar convection zone, and you see here in low latitudes kind of these branch which kind of extends somewhat into the convection zone. We don't know how deep it really goes because the sensitivity is very poor towards the lower parts of the convection zone. And you have stronger changes in the differential rotation near the poles. And some of this is likely due to some feedback of the dynamo-generated field on the differential rotation. Since the differential rotation induces a lot of magnetic field, you expect the Lorentz force feedback actually to work against it. And if you do models which include this Lorentz force feedback, you do get some of these variations at least. The low latitude branch is more difficult to get. And these torsion oscillations cannot just be seen by helioseismology, they also can be seen in surface Doppler measurements, which is actually done here. You see here, this is again the zonal component, the differential rotation modulation, but you also see this is the meridional component where you do see flows moving away from the equator towards the poles. There is also some imprint of the active region belt on these large-scale flows. Yeah. 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 I think for the helioseismology, for these ones, I thought, isn't they normally do something like 100-day averages or something like this, at least to get these deeper reaching flows? And of course, if you do these surface measurements, I mean, you have to want to at least average over enough individual sunspots. For example, some of these flow patterns you see in the meridional flow, they are kind of maybe related to larger scale inflows into active regions. So you definitely have to average over multiple of those, that you don't just see the individual flow into active regions, but really the impact on the mean flow pattern. But I thought the helioseismology is typically something like 108 days, if I remember it correctly, what they typically do. So if you want to construct the solar dynamo model for the sun, what's really the goal is? I mean, the goal is really, the model should kind of explain the solar-like activity pattern in terms of having the cyclic behavior, the equator-ward propagation of activity, have surface flux evolution consistent with observations, have the large-scale flow variations with consistent with observations. And then if you want to go a little bit further, also show a solar-like amplitude variation from cycle to cycle, and maybe even go one step further and trying to actually predict the future activity. So, but the honest answer is that most models already struggle a lot just with the part one. So in this talk, I will mostly focus on part one, how we actually understand just the basic activity of the sun. But nonetheless, trying to explore, for example, why different cycles have different amplitude certainly provides you with some additional constraints on how these dynamo models actually might operate. So what are the basic ingredients we are having? We have large-scale flows. Most obvious ones are the differential rotation, the meridional flow, which is kind of these large-scale conveyor belt-like flow. We strictly only know that it's definitely poleward in most of the near-surface layers. Where exactly it returns, and if there's just one big structure in the convection zone, or if there are multiple cells, that's still open to debate. And then, in addition to having these mean flows, they also do have some cyclic variations. Then we have various turbulent induction effects. We have transport effects like the turbulent diffusivity. Advective transport is the turbulent pumping. Then we have effects which enable the dynamo, most prominently the alpha effect. But then if you look in more detail, I mean, if you look in the photosphere, you don't just see a large-scale homogeneous mean field. You actually see that the field is actually made out of these individual field of sunspots. So there is some organization actually on smaller scales. So really what you also want to understand is how the dynamo produces a large-scale field, but how this actually then leads to flux emergence, that some flux loops move towards the photosphere and form something like sunspots. And actually, as I will show, there are some theories which actually think that it's actually this process of having sunspots forming in the solar photosphere, that is actually a critical component to the dynamo itself. It's not just a byproduct of the dynamo. In some sense, these sunspots moving into the photosphere, they typically have a systematic tilt angle where the leading polarity is closer to the equator than the trailing one. And this on its own leads to something like an alpha effect, since it requires some twisting motions, and that's called the Becker-Clayton mechanism. And that alone can actually explain a lot of the activity we do observe. The modeling approaches we have are mean field models where we solve equations for the mean field, mean flows and mean magnetic fields. They are much less expensive, but the problem is you need to have good models to actually describe all these mean field induction coefficients I just talked about in the previous lecture. In some sense, these models are not typically from first principles because they have a lot of degrees of freedom. You need to have some underlying turbulence model to derive these mean field coefficients. The other approach is 3D numerical simulations. They solve the full set of equations, but they're also not from first principles because they're very expensive. So it's challenging to run them for long enough to understand something like a solar cycle, right? The cycle is something like 11 years. You really want to run them over multiple cycles, which is expensive. So you have to compromise on the resolution, or you do high resolution for short periods, but then you cannot capture a full cycle. They do give some understanding of dynamo ingredients, but we are not at the point is where you just do the most obvious thing. You just take a rotating convection zone, you drive a solar luminosity through it in terms of energy flux, you rotate at the solar rotation rate, and just something which looks like the sun comes out of it. That's typically not happening in these models. Now, with advances in computing, of course, this balance is shifted more and more towards 3D simulations, but at this point, we are still needing both. So let's go to mean field models. So one thing you have to keep in mind is when you do mean field models, you only consider average quantities. So in some sense, sunspots are a key feature of the solar cycle because it's the most obvious thing you see if you look at the sun, but mean field models just average over them. So you have to keep that in mind. You cannot really capture something on that scale. The other problem is really, if you go back to these basic assumption mean field theory that you can express these turbulent electromotive force as some expansion of the mean field, even if you just go to these first order in the derivatives, formally you have here 36 mostly unknown functions of R and theta in the convection zone. There's enormous amount of degrees of freedom here, and they're not trivial to compute from first principles. So typically, mean field models, they use strong simplifications for this, like a scalar alpha effect, just a scalar turbulent diffusivity, to explore kind of the type of possible solutions are there. But once you want to go to fine tuning, you're really getting lost in degrees of freedom. You can compute these mean field coefficients from 3D simulations, and there have been a lot of work about this in recent times. And what they typically show is when you do this consistently, and what you essentially do is you run a 3D simulation, but instead of just solving one induction equation, you actually solve an additional number of induction equations with imposed mean field. And these induction equations, they are just diagnostic equations to measure if you impose a certain mean field, what are the induction effects you're getting? And by solving enough of these additional induction equations, which is called the test feed method, you can get in the end enough constraints to actually compute all these coefficients from your dynamo simulation. And what they typically find is you pretty much need all of them. And if you do this, you can end up with a mean field model, which has solution very similar to what you had in a 3D simulation, but you really need all these coefficients, which makes it very impractical to really use this as an approach to model the solar dynamo from first principles, but it can be also a very useful approach to actually understand what's going on in your simulation. So when we look at the solar differential rotation pattern, it kind of became very obvious that there are some interesting regions on the sun, like you have these strong shear layer at the base of the convection zone, and you have this near surface shear layer. So people very quickly focus their research on kind of understanding it. What are the different contributions from these different shear patterns? You can have dynamos which operate in the bulk of the convection zone. They have mostly latitudinal shear. You can have dynamos which operate at the base of the convection zone where they have radial shear, or you can have near surface shear layers where you again have radial shear. So a lot of uncertainties are really where you have the location of the dynamo, where does the alpha effect really work, and what is the turbulent transport, and what is the role of the meridional flow, right? These large conveyor belt flow, which kind of works together with the turbulent transport mechanisms to transport magnetic field in the convection zone. So the first model I quickly want to talk about here are kind of these thin layer dynamos, like dynamo which operates in the shear layer at the bottom of the convection zone. And if you solve the dynamo equations and put in a shear like the solar-like shear, you end up with these sort of dynamo solutions where you see propagation in latitude. But the problem is, since the radial shear in high latitudes and low latitudes is opposite sign, you actually get the propagation, two bands of propagation. One propagates equatorwards, one propagates polarward, which is not exactly what the sun is showing. Another problem you very often see with these thin layer dynamos is when you look here that the length of the dynamo wave here is, the wavelength is pretty short. It's roughly comparable to the depth of this thin layer. If you look at observation of the sun, you basically see these extended butterfly wings, and you typically see only one of them at any given time. But once you constrain a dynamo to a thin layer, you can see a multitude of them, which is not exactly what the sun is doing. And this propagation is a big problem because depending on what you're doing, if you take the most basic kind of model with an alpha effect, which is proportional to the cosine of the latitude, you mostly get this polar branch, which propagates equatorwards, but you don't see much happening in low latitudes. You can, if you constrain this alpha effect a little bit closer to the equator, you can get a low latitude branch, but it propagates in the wrong direction. If you then switch the alpha effect around, you can in the end get something in low latitudes which looks solar-like, but you still have this strong polar branch which goes the opposite way too. And so you kind of see here, I mean, this was kind of, before there was any observation of differential rotation, people just made up a solar interior rotation pattern they thought is meaningful, and everything looked fine. But when helioseismology really nailed down differential rotation, all these models got into big trouble. Yes, yes. Typically, this is in some dimensionless units here. So, but I mean, yeah, this is kind of, you see, kind of, this would be, in the sun, this would be 22 years, for example, from here to here. And so in some sense, you can sort of make it work if you kind of squeeze the alpha effect, restrict the alpha effect to low latitudes, and you have to change the sign. Now, the sign change is not necessarily unexpected. I mean, the problem in the northern hemisphere, the kinetic helicity is negative, which means you have a positive alpha effect. But that is mostly in the bulk of the convection zone. Upflows expand, downflows contract. But if you get to the bottom of the convection zone, because you have there a boundary condition, downflows eventually have to expand. And that changes actually the kinetic helicity in the convection zone. So if you do have a model just operating at the base of the convection zone here, it's not necessarily unexpected that maybe the alpha effect might be negative. But the problem is, of course, you have these high latitude branches, and very often you have a little bit too much overlap between neighboring cycles, which isn't what the sun exactly is showing. Now, then there's a large amount of dynamos which are more distributed over most of the convection zone. And the model which has really gotten a lot of attention over the last 10, 20 years is what people call the flux transport dynamo. And here the idea is you have this meridional flow, this conveyor belt flow forward at the surface. So somewhere there has to be an equatorward flow. So people were thinking, how about you add a flow in there, and you can get solutions like the one shown here, where you have this forward flow, it's equatorward at the bottom of the convection zone. It's actually this advection effect which pushes the magnetic field towards the equator. And this class of model has been actually quite successful in producing the solar-like behavior. And most of the time, they mostly have an alpha effect, which is constrained to the near surface layer to just mimic what actually sunspots are doing. When sunspots are rising towards the surface, you have Coriolis force acting on the rising magnetic flux bundles. And what that typically means is you have these systematic tilt angle where the leading polarity is closer to the equator than the trailing one. That is kind of indicated in this schematic. You do have differential rotation producing toroidal field from the poloidal field. Then you have some of these flux rising to the surface, and you have the Coriolis force tilting these spots. And then you have, due to these tilt angles, the leading polarity has a higher probability to actually reconnect across the equator and partially cancel across the equator from the trailing polarity. So in the end, you have the meridional flow preferentially transporting the magnetic field from the trailing polarity to the poles. And that essentially regenerates then the polar field, but it has then, after you go through a cycle, it has the opposite sign. And then you start the same process again with the opposite sign. And these entire class of models are called Babcock-Layton flux transport dynamo models. And in general, they do have a good agreement, but still a lot of models have kind of these activity cycles which start in too high latitude. You still have to kind of come up with reasons why you only see the lowermost tip of this activity pattern. But as other mean field models, you have a strong sensitivity to many ingredients. And really one concern in these models is, what is really the structure of the meridional flow in the solar convection zone? It's forward at the surface, but the structure of the flows in the convection zone is still heavily debated. I mean, typically mean field models, they assume these really nice flow sails like indicated here. If you do numerical simulations, this is actually one of the nicer looking ones where you have mostly a single flow cell, but you already see there are some, particularly near the base of the convection zone here, some patterns of counter cells, and also you have something here near the surface. But one big problem with these models is you have kind of, in order to have the meridional flow being able to transport the magnetic field, you need the turbulent diffusivity, which is low enough so that it's advection dominated. Turbulent diffusivity is something like a scale height in the convection zone times the turbulent RMS velocity. So you typically these models have to assume a low turbulent diffusivity, which you can only get if the RMS velocity in the convection zone is somehow lower than you expect it to be. But there's another problem is, in order to enable or maintain the meridional flow velocity through some turbulent transport processes of angular momentum, you also get the meridional flow speed, which depends on the RMS velocity squared over the rotation speed. So if you bring this down, you also bring the meridional flow speed down. So you're kind of stuck in there. You cannot just lower the turbulent diffusivity without also getting a too low meridional flow speed. Some models can partially compensate for this by having a strong radial turbulent pumping, which kind of keeps the magnetic field kind of pushed towards the lower part of the convection zone, where the flow is assumed to be equatorward. Now the problem is, if you use helioseismology to kind of infer what is actually the flow in the deeper convection zone, it's not that clear. I show here two helioseismic inversions. The surface layers have a poleward flow. That is the one thing they all agree on. But this inversion, for example, shows an equatorward flow here in the middle of the convection zone, again a poleward flow at the base of the convection zone, whereas this more recent inversion actually shows something which is more the single flow cell. But some of these models, for example, they also put in constraints like divergence rho v equals 0. Some of them are just straight helioseismic measurements. This is an example of an inversion which actually put in this mass flux constraint. Then some of the inference in the deeper layer is not really a direct measurement. It's something which you get out of the mass flux constraints. And even using different instruments, some of these flow structures are really even sensitive to details of the measurement. So this is still a big open question. Now, one other complication is, even if you would know exactly what the meridional flow is, there is this additional turbulent transport, this gamma term I introduced in the last lecture. The dominant component of this term is the radial transport. But when you are in a rotating system, the gamma effect itself can also have latitudinal transport. So you also have these additional turbulent transport processes which can actually add to the transport of magnetic field. So there's a lot of uncertainty, a lot of assumptions you have to make to actually get these models to work. So why not just doing 3D simulations, right? We know the equations, just don't make any assumption or shortcuts. You just solve the equations, including differential rotation, meridional flow, and all the nonlinear effects are automatically included. But even that approach has some intrinsic limitations. You do have to deal with your boundary conditions in the radial direction. You have this bottom layer of the convection zone where you form the shear flow. You have the transition towards the radiative core. You go from a convective regime to a strongly subadiabatic regime where you suppress convection. That boundary layer is not easy to properly address. The top boundary, because these models, they cannot typically deal with a density contrast of 10 to the 6 in the solar convection zone. They leave out the top layers. So you're not really dealing with the photosphere. A big problem is you cannot capture the Reynolds numbers of the sun, like magnetic Reynolds numbers of 10 to the 9, fluid Reynolds numbers even 10 to the 12. So you have to do something to the small scales. You either use a direct numerical simulation where you actually use the correct expressions for the dissipation functions, but you have to use dramatically increased diffusivities to actually make the simulation work. Or you do some sort of implicit large eddy simulations where you mostly use numerical terms to stabilize your system, which means you introduce diffusivity just near the scale of the grid and keep the large scales mostly untouched as much as you can. But even with doing all that, they're very expensive. And they provided some understanding of ingredients of the dynamo, but no complete picture yet. Now, the first simulations in rotating bodies have been done 1981 by Gilman and Miller. And some of these really early simulations really add low resolution. I mean, at that time, what you could do is something like 32 grid points cubed, or maybe 64 on a good day. That's something you can run, could in principle run on your cell phone nowadays. And some of these early models actually look pretty promising in the sense that they produced already large-scale field and periodic reversals, even though the propagation of field was not always that equatorward. There has been a little bit more success with these models for the geodynamo, and I talk about this in the end of the lecture. Doing these 3D solar dynamos started kind of in 2004, and these early dynamos, they mostly showed pretty much a big mass of field without too much solar-like activity behavior, instead of having a nice cyclic behavior and a dipolar field on the large scales. But at later times, at least, people found that by actually spinning up these simulations a little bit, by modeling a fast rotating star, they could get magnetic field a little bit more organized in the convection zone. Some of the models, they even included a tachocline, and they could find some more organized field at the base of the convection zone. This is an example where you have these large-scale toroidal bands produced with opposite polarity in each hemispheres. But the interesting thing is they only found this activity pattern after speeding up the rotation in these simulations, not so much for solar rotation rate. And this is shown here, where studies were done changing the rotation in these simulations. It mostly found cyclic solutions for faster rotation, but there's kind of this area around the solar rotation rate where it was very hard to actually get a dynamo excited, which is a little bit odd. Why should it be particularly hard for something like a solar-like rotation rate? This is another example of a simulation which did show a 33-year period feed generation in the bulk of the convection zone. And most interestingly, it actually did show something which looks like a butterfly diagram, where you had these equatorward propagation of activity belts with, I mean, the symmetry is not exactly dipolar here. There's some phase shift, so you have some superposition of a dipole and a quadrupole. But there was one interesting thing I wanted to point out here, that when you do these 3D simulations, you have to be aware that sometimes these nonlinear feedbacks, once the Lorentz force gets strong, can have a dramatic impact. So this simulation was started from a weak seed field, and you see a dramatic difference in the behavior of the simulation in the early phases when the magnetic field was weak. You had these extremely short cycles, or not even cyclic behavior at all. And then as the feed became strong, you suddenly transitioned to this regime where you had this nice equatorward propagation. So it's kind of, it was a phase transition which was caused by feedback of the Lorentz force on the flows in the system, which is something which is very difficult to capture in any mean field model. If the sun is doing something like this, you really can only do this in a 3D simulation. And more recently, there have been a couple of simulations which were able to actually build up toroidal field in the convection zone of a sufficient strength that they actually could see magnetic field rising in flux bundles towards the upper boundary of the simulation domain, which isn't the photosphere. It's typically at least 20 megameters down from the photosphere. But at least these dynamos, they started to make some connection to what we actually observe on the sun, that you have magnetic flux poking through the surface in form of sunspots. Now, the kind of flux loop you get in these simulations, they're typically a little bit too large scale for solar active regions, but at least these simulations started to move in the right direction. So just to summarize a little bit, a lot of different groups have found in recent years cyclic dynamos with periods somewhere in the 10 to 60 year range. Some of them have equatorward propagation of activity, but there's no simple explanation necessarily for the cycle lengths and the magnetic patterns, and because the cycle length can be a nonlinear effect where really the Lorentz force feedback plays a critical role in establishing that. And even for those models which do have the equator about propagation, looking in detail, you don't necessarily get this for the right reason. Essentially analyzing why in the simulation you had equator about propagation had to do with the fact that the differential rotation in these simulations were not quite solar-like, and you wouldn't necessarily expect this for solar-like differential rotation. The big contrast to mean field models in these 3D simulations is there's in general no single dominant turbulent induction term. If you want to derive these mean field coefficients from these simulations, you pretty much need all of them. And the nonlinear feedback is really critical to even get sometimes these cycles right. So in some sense, we have a situation where both mean field models and 3D simulations have quite serious challenges in actually providing a consistent model for the sun. Well, there's another approach. We could just, let's try to do the most minimalistic thing and just ask actually, what do the observations tell us? The most minimalistic approach here. So the one thing we know that if you correlate the strength of the polar magnetic field to the strength of the next cycle, that it has you find actually a pretty good correlation. So here all the points on these in this plot are essentially the strength of the polar field over all these different cycles, and then related to the strength of the next cycle in sunspot number. Now the problem is we don't really have good measurements of the polar field except for the most recent cycle where you actually could measure magnetic fields directly. So what was done in this plot, they actually used disturbances to the Earth's magnetic field, so the solar wind, the AA index, which is related to the polar field of the sun, to actually infer what the polar field of previous cycle was. So in some sense, what this correlation shows is really that the magnetic field at the polar caps, the poloidal field, you see that this is really the source for the toroidal field, which is wound up by differential rotation to produce a next solar cycle. And then there is this nice work by Robert Cameron and Manfred Schüssler, where they pointed out that actually all you have to know is really what is the magnetic field, so the radial magnetic field at the solar surface, and what is the near surface differential rotation. And you can exactly compute what is the net toroidal flux in the hemisphere of the sun. And essentially, you take the induction equation, dB dt is a curl of E, you integrate this over the entire hemisphere, and that integral of dB dt gives you the time derivative of the toroidal flux in the entire hemisphere. And then you have essentially this integral of the electric field over the boundaries of the domain. Pretty much this polar part and the part at the base of the convection zone doesn't matter because you can move this far enough inwards that there isn't much field. The part here at the equator needs just to some exchange between the hemispheres, which you can model easily. And then you just have the surface integral, which you actually know exactly what it is, because that is pretty much given by observations. You just need the surface differential rotation. You need the radial field at the surface. And this decay term here, that is just coming from the exchange across the hemispheres. And if you then just take the observed differential rotation, the observed radial field, you can use this equation to actually compute what is the expected toroidal field in the hemispheres of the sun, and you compare that essentially to what you get from observations, which you can get from the magnetic field, which actually appears on the solar surface in form of sunspots. And what you see is that these two things actually look quite similar, which strongly suggests is that really you can pretty much constrain the net toroidal field produced in the convection zone by just having knowledge of the surface term. So the question is this all we need, or do you need some additional dynamo effects in the solar convection zone? Now the thing is here, this is the net toroidal magnetic flux. If you have any additional dynamo effect, which is kind of buried somewhere in the convection zone without making any connection to the surface layers, that one will not give you a net toroidal flux, because you get this net only by having this contribution from the surface term. It would essentially produce a mixed polarity toroidal flux in the convection zone. And there are some constraints against this, because the sun actually follows these polarity rules pretty well, like Hale's polarity rules, the polarity of sunspots groups in the hemisphere. You only see a very few exceptions from these rules, which strongly suggests is that the toroidal field in the convection zone is dominated by one polarity. So you wouldn't expect too much contribution from something which is just buried in the convection zone. So essentially, you start with what the sun tells us, which is the polar field is strongly correlated with the strength of the next cycle. So that means it must be connected to the polar field, which is converted to the toroidal field via differential rotation. The sun generally obeys Hale's polarity rules with only a few exceptions, which means the toroidal magnetic field in the convection zone is likely mostly unipolar. And the surface term, which is observationally constrained, essentially this back-latent source coming from the active region evolution, pretty much is sufficient to produce a toroidal flux with a sufficient amplitude to explain the solar cycle we're observing, which strongly suggests maybe you don't need much additional alpha effects somewhere operating in the convection zone, and they anyway would only produce a mixed polarity field. It goes even further. There are some observed nonlinearities in the near surface layers. For example, you have inflows into the active region belt. What these inflows do is they essentially keep the magnetic field constrained in the active region belt, which means the two polarities of an active region, they can locally cancel each other more, which means there's less magnetic field left over to actually produce the new polar flux. So you even observe the non-linearities. And the regularity of the cycle suggests that you have a weakly supercritical dynamo with just some noise, and the noise is mostly the active region evolution, the randomness in the way sunspots form. So if you actually, I don't show it here, but actually if you use kind of a low order dynamical system model, you pretty much can explain really the long-term variability, at least in a statistical sense for the sun. And this is all things the sun tells us. You don't have to make any assumption. The only assumption you have to make is really that wherever this toroidal field is in the convection zone, you do have some transport process, may it be merely on a flow or some latitudinal turbulent pumping, which pushes the magnetic field towards the equator. That is the one assumption you have to do. So the question is, do we need anything else, or is the sun just doing this? And well, if the answer is no, then you have to find reasons why all these other dynamos, which you very often find in either doing mean field studies or doing 3D simulations, they don't seem to operate on the sun. So what is so special about the sun? And in recent years, people actually have found a few things actually called conundrums, which actually puts the sun in a somewhat special place. So one thing is differential rotation, right? You do these 3D simulations, you pump a solar luminosity through them, and you spin them at solar rotation rate, you get turbulent angular momentum transport, which creates some differential rotation in these 3D simulations. But the sign of the differential rotation you're getting actually depends on how strong the influence of rotation is. There's a dimensionless number which measures this, which is the Rossby number. And there seems to be in the strong rotation regime, you do get differential rotation, which actually does have the sign as we have it on the sun. You have a fast rotating equator, a slow rotating pole. But if you go to weak rotation, you get the swap to anti-solar differential rotation, and this happens roughly at a Rossby number of 1. The problem is the sun is pretty much right near this transition. So whether you get something solar-like or non-solar-like really depends on, do you end up a little bit more here or do you end up a little bit more there? And there was another thing related to this, what people realized also in the last 10 years is that it looks like that the sun actually has rather low convective flow amplitudes on the larger scales, the solar convection zone. So what I show on this plot is, it's a velocity spectrum, which is essentially takes the power spectrum of the velocity times the wave number square root of it. It gives you essentially velocity amplitude as function of scale. Here at a wave number of about 1000, that is where granulation is. Here you have a bump at about wave number of roughly 100 or so. This is where supergranulation is. And then towards large scales, this velocity drops quite substantially. At L equal 10, you have roughly 10 meters per second. Now I overplotted here a couple numerical simulations of convection. All these models, these are high resolution simulations of just photospheric granulation. They agree pretty well in general with these observed flow amplitudes. But if you go to these larger scale models, the deeper convection zone, the concerning thing you find is that they typically have flow velocities on the order of 100 meters per second at L equal 10, about a factor of 10 more than the sun seems to have. And that means is when you do these 3D simulations that the flows are much less rotationally constrained than they should be. So in some sense, you end up too much in this part of the regime, but you should be here. It's currently not fully understood why this is actually happening. There seems to be something very fundamental about highly stratified convection we do not get right. And also, if you just use mixing length theory, which typically stellar evolution codes use, mixing length theory is also somewhere up here. There are indications that for reasons we do not fully understand, convective flow amplitudes in the sun on larger scales are at least an order of magnitude lower than they should be. Okay, I leave it for now there. I come back to this, but now just I would like to talk a little bit about the quiet sun magnetism. So really, if we go away from active regions and just try to understand really how does the magnetic field look like at the smaller scales? And where does the magnetic field come from? But also, does the small scale magnetic field actually have any consequences for the convection, differential rotation, and even the large scale dynamo? And these simulations of quiet sun magnetism, they started about 25 years ago and have been improved over the years. And I just show here a very quick timeline of what has been done. And these are all 3D convection simulations. The early one were just incompressible. But then starting here, at least from 2007, these were more realistic simulations. We actually have radiation transport in the photosphere. So we actually get granulation patterns which look pretty much like the granules on the sun. They do have a realistic equation of state which account for partial ionization in the near photospheric levels. And these models have been compared really in detail to observations. And what you have to do is you have to do the full forward modeling. You start from the model atmosphere, you compute what you would see in spectral lines which are sensitive to magnetic fields through either the Zeeman effect or the Hahn effect, which is scattering polarization. And through this, you can account for a lot of resolution-dependent effects, like when you have the Zeeman effect, you have partial cancellation of the polarization signal. You don't see all the magnetic field which is there. So through the forward modeling, you have to account for this. So people kind of have converged that the strengths of this quiet sun field is something like 60 to 80 Gauss for the vertical field at optical depth unity, so kind of the deepest layer we can see on the sun. So this seems to be actually very weak, at least compared to sunspots, which have something like 3,000, 4,000 Gauss. But you have to keep in mind, this is magnetic field which is present on the solar surface everywhere all the time. So if you just take these 60 to 80 Gauss and you integrate this over the entire surface of the sun, so these hidden mixed polarities, this is no net flux, this is mixed polarity field. You just integrate the absolute value of the vertical field. You end something up with something like 4 times 10 to the 24 Maxwell. And this is a very large number. A typical solar active region or a sunspot is something like 10 to the 22 Maxwell. So this is something like 400 sunspots. So with an effector of a few, the mixed polarity field we see in the photosphere at any given time is something like you take the entire 11-year sunspot cycle, you take these sunspots, you shred them into tiny pieces, you mix both polarities together and sprinkle them over the solar surface. That is what the quiet sun is doing all the time. And because this magnetic field exists actually on very small scales, it decays very quickly. So you have to do this really on time scales of minutes to hours. So in some sense, it gives you an idea that actually what's going on in the quiet sun energetically is much more dramatic than what's actually happening on large scales building the sunspots. And this tells you already right away that we really need an independent dynamo like these small-scale magnetic dynamos I introduced earlier this morning to maintain this magnetic field. You cannot have this just as a leftover from the large-scale dynamo. So these are some examples of small-scale dynamo simulations in a small box of granulation. And this is a snapshot from these simulations when they're in their kinematic growth phase. Typically, they are initialized with some really weak field, 10 to the minus 3, 10 to the minus 6 Gauss. And you do get magnetic field on the smallest possible scales you can resolve. If you look at the power spectrum, it peaks somewhere towards these smaller scales. But as these magnetic fields saturate and become stronger, the magnetic field becomes organized on larger scales comparable to granulation downflow lanes. And you see this in the magnetic power spectra kind of having their peak more near where also the kinetic energy spectrum peaks in granulation. These dynamos, they grow very quickly in the kinematic growth phase, and the higher the resolution, the faster they grow. This is a bunch of small-scale dynamo simulations ranging from 32 to 4 kilometers grid spacing. In these 4-kilometer case, the growth rate is something on the order of minutes, so it's really fast. When we look at the sun, we never see the kinematic growth phase because it's really fast that the dynamo grows through this. And once you reach a strength, which is something like 10% of the average field strength of the quiet sun, you already move out of this kinematic phase and go to a much slower saturation phase of the dynamo. And in the saturation phase of the dynamo, you also get a small but still significant fraction of magnetic field with a strength of about kilogauss. So the small scale field on average is weak, but you can have some kilogauss field in there as well. And this is an example how some of these small scale dynamo simulations look in detail. This is a simulation which has 4 kilometers grid spacing, which is way smaller than what we can currently observe. With DKISS, the solar telescope on Hawaii, you could theoretically observe down to scales of something 20, 40 kilometers if you really get diffraction limited. But very often you have atmospheric turbulence, which actually brings the resolution down a little bit from that. So something on the scales like I show here has not yet observed on the sun, but there is some hope that we're getting much closer with that in the near future. Now, these are all simulations which are just concerned with the top layers of the solar convection zone, which means they do have some bottom boundary here, which is not the real boundary of the convection zone. And one big challenge with these simulations is you have to make some assumptions about what you do in inflow regions. Typically, these simulations use open boundaries to mimic that actually the convection zone is 200 megameters deep. So you do have plasma crossing the domain. You know exactly what goes out, but you have to make assumptions about what's going in. This is what I show here. These are just two simulations where you made two different assumptions. On the left side, you assumed the magnetic field strength in inflow regions is 0, and this is truly a dynamo which just operates in the uppermost few megameters of the sun. Whereas in this case, there was an assumption that the inflows are magnetized, and you expect this to happening because all these downflows which go out with strong magnetic field, eventually they hit the base of the convection zone, they have to turn up and they're still magnetized. And there's dynamo action even on deeper scales in the solar convection zone. And it turns out that it's actually critical if you don't account for it, you saturate at a weaker feed strength, but if you have these deeper recirculation component, you end up with something which is comparable with observation. So what we essentially learned from these simulations is that the solar small-scale dynamo is really operating over a wide range of scales, not just the photosphere, really multiple scales throughout the convection zone. And what it means also is that the stratification leads to an organization of this magnetic field on larger scales. That is actually observed in the quiet sun. This is an example of a Hinode magnetogram from the last solar cycle, that solar minima at around 2008. You kind of see the salt and pepper feed on small scales, but then you also see this network feed on scales of supergranulation. If you do a small-scale dynamo simulation in a big box, right? This is now a 20 megameter deep box. Here you drive convection structures which have supergranulation scales. You also in these small-scale dynamos can get a mixed polarity network on larger scales. So there is certainly contribution from a small-scale dynamo even on the organization of magnetic field in the photosphere on the scale of supergranulation. And just to illustrate this one more time, if you make a simulation in a small box, this is what you get. This is 6 by 6 megameters. You mostly see granules with weak field and intergranulanes with strong field. As you increase the box, you can get some larger scale voids with weaker field, and you start producing some kilogauss strength network fields. And if you go even to 100 by 100 megameter domain here, you have some of these void-like structures even on scales of 10 megameters or more, and you have really these strong patches of kilogauss field. So even a small-scale dynamo can produce this, and this actually matters. You can actually combine these sort of dynamo simulations with a simulation which goes all the way into the corona. If you do have these small-scale dynamo with a deep recirculation which produces these supergranular network structure, you do get a quiet sun on top of this. And here this shows synthetic AIA emission computed from a simulated corona. You can compute the total radiative energy loss you would get in the simulation. And the number is within a factor of 2 comparable to typical estimates of what the quiet sun is actually doing on the sun. If you don't have this deep recirculation, you constrain this dynamo only to the near surface layers, you still maintain a corona, but it's very wimpy. In this case, the radiative energy loss dropped roughly by a factor of 60. So having these deep-seated small-scale dynamo on the sun is sufficient to even maintain a quiet sun corona. Okay. So I mentioned before that really the quiet sun seems to be very energetic, kind of. Just by looking at these rough estimate of numbers, it looks like you do the 11-year solar cycle pretty much every hour or so in the quiet sun, which raises the question, how much energy do you actually need to do this? And you can use these 3D simulations to estimate this. So what I show here is for some of these near surface high resolution simulations, they go just 1.5 megameters beneath the photosphere. I show here a couple of the terms which show up in the kinetic energy equation. So the primary driving term of convection is the pressure buoyancy driving. This is work done by pressure gradients and the buoyancy force, which is here the solid blue line. This peaks just a little bit beneath optical depth unity, which corresponds here to 0. Most of this energy goes into acceleration of downflows in the intergranular lanes. And that shows up as the negative divergence of the kinetic energy flux, which is the blue dotted line here. If you combine these two terms, what is left over is this solid black line. This is kind of the driving, the turbulent driving, which is left to do anything else like running a dynamo. And the question is, how much of this energy is actually used up by the small-scale dynamo? And what I show here is the negative Lorentz force work, this term here. And what you see here is it depends now on the magnetic Prandtl number. If you have a high magnetic Prandtl number, the Lorentz force only takes a very small fraction of these total pressure buoyancy driving, which doesn't go into acceleration of downflows. But if you lower the Prandtl number in this simulation, I could go to something like 0.1, it already gets pretty close. Now, the sun has a Prandtl number of 10 to the minus 5. You can likely safely assume that pretty much all of the available pressure buoyancy driving here is pretty much absorbed by the small-scale dynamo and turned into magnetic energy. These Prandtl number dependence of these energy conversion rate has been found in more general magneto-convection turbulence simulation, including large-scale and small-scale dynamos. It seems to be pretty universal. If you have a high magnetic Prandtl number, most of the energy is dissipated through viscosity and very little through a dynamo and resistivity. But if you lower the Prandtl number, most of the energy is converted to small-scale field through the Lorentz force and then dissipated through magnetic resistivity. There's very little left for viscosity to dissipate. Now we have this number here now, which is something like 150 ergs per cubic centimeter a second, which is kind of being dumped in the dynamo. You can integrate this over the entire solar surface. And if you just do it for these uppermost 1.5 megameters, that's a third of the solar luminosity, which goes into maintaining the small-scale magnetic field on the sun. This is a pretty large number. And this is just the upper 1.5 megameters. There's more happening in the rest of the convection zone. How much this adds depends in the end what is the total pressure buoyancy driving of convection, which we don't exactly know. You could take a mixing length model and it would be something like 3 solar luminosities. But you might wonder, does it even make sense that this number is actually larger than the solar luminosity? But keep in mind, this is not the sink of energy. This is energy which pressure buoyancy driving creates turbulence. The kinetic energy is converted to magnetic field through the dynamo process. Then that energy is dissipated through resistivity, goes back to the internal energy, and then is again available through pressure buoyancy driving to drive convection again. That happens on every scale height in the sun. You have certification of 10 to the 6 in the solar convection zone. So these can add up to a large number. So energetically, it looks like this small-scale dynamo is actually extremely powerful machine, which pretty much takes all the available pressure buoyancy driving in the convection zone to turn it into magnetic energy, which is then dissipated through resistivity, which raises the question, if it's so energetic, does it actually have effect on even larger scale things in the convection zone? And this is now we are really getting here to what is really very active research. So not all of this is completely settled. There are some simulations which show this, but not all of them do. But this is a very impressive simulation which has been done just a couple of years ago by Hideyuki Hotta and Kanya Kusano. This is now a global simulation of a rotating shell, but it has high enough resolution that you have actually a very efficient small-scale dynamo operating in there. In principle, you could also have a large-scale dynamo, but at least for the time the simulation was run, there was no indication that it actually produced a large-scale field. And you kind of can see here already that it looks like you have a fast rotating equator and a slow rotating pole. I mean, this is in a frame which moves with the mean rotation rate. So you see here the rotation in the opposite direction because in this co-rotating frame. So one interesting thing which was found in this simulation that you only get these solar-like looking differential rotation once you have high enough resolution to have a really efficient small-scale dynamo in there. So they did the simulation at 3 different resolutions. At low resolution, they pretty much found more a fast rotating pole, slow rotating equator. And only when they went to the high resolution case, they had the fast rotating equator and slow rotating pole. Interesting thing is, if they stayed at the high resolution and they zeroed out the magnetic field and did a purely hydrodynamic simulation, differential rotation swapped sign, and you had again a slow rotating equator and a fast rotating pole. So there's some indication that all these small-scale field produced by a small-scale dynamo here is even essential for getting differential rotation right. And one other interesting thing the simulation showed is that it actually reduced the convective power on large scales. So here it shows solid lines are the kinetic energy spectra for these three different resolutions. The dotted lines are the magnetic energy spectra. There is a moderate increase of magnetic energy for the highest resolution case, but the most dramatic effect was that actually the kinetic energy on large scales dropped by about a factor of 10. And this is all from small scale field. And this is essentially what enabled this dramatic difference between these two cases. There are two things happening. By having reduced energy on these large scale flows, they are more rotationally constrained. This leads to some deflection of the convective energy transport towards the poles, which leads to a pole which is about 5 to 10 Kelvin hotter than the equator. This temperature difference allows you kind of to avoid these contour lines of omega being aligned with the rotation axis, and you get to something which is more looking like actually what the solar difference rotation shows. The other thing is that the small scale field produces Maxwell stresses which also transport angular momentum. And the transport of angular momentum by the small scale field has the opposite sign as the Reynolds stresses. And so when you get in this regime of strong magnetic field, it's actually the Maxwell stresses which flip around the sign of differential, the angular momentum transport, and that way you get the solar-like differential rotation. Now, this drop of energy on the large scale is an interesting effect because I mentioned to you previously that we have these convective conundrum on the sun that it looks like that all simulations produce too much convective power on large scales compared to what we actually observe. And the interesting thing is at least that these small-scale dynamo simulation with a very strong small-scale dynamo at least showed some drop of energy on large scales. You would have to go at least another order of magnitude to get consistent with the sun, what the sun is doing. But at least there's some indication that you actually may have to understand the small-scale dynamo to actually get all the large-scale behavior on the sun correct. So really an example here how the smaller scales are really coupled to the larger scales in the system. Okay, let's move a little bit from the sun to stars. So you may wonder, if you don't even understand the solar dynamo, what's the point of going to other stars where we have even less detailed observations? But of course, this is interesting because the sun is only a single realization of a stellar dynamo in a certain corner of the parameter space. And it's worthwhile asking, how typical is it actually? And we cannot easily extrapolate from the sun to other stars because of all the uncertainty we have about how the solar dynamo works. But by looking at the stars, we see how these dynamos operate dependent on the stellar structure, like the convection zone depths, right? If you go to lower mass stars, the convection zone depths relative to the radius of the star increases in depth until you get fully convective stars. And most importantly, stars have very different rotation rates. So some of them are much more strongly rotationally constrained than the sun. And I showed you before, one challenge is that the sun seems to be very close to this Rossby number 1 transition, where you even have the swap from solar-like to anti-solar differential rotation. So people have looked into this, and I just want to highlight a few critical results here and don't go into too much depth. So one very solid relationship which has been established by looking in other stars is these activity rotation relation. And what is shown on this plot, these are all observations of magnetic field on other solar-like stars. Bigger dots correspond to more massive stars, small dots to much more lightweight stars. And what people see is that when you are, and this is shown as function of Rossby number, the sun is somewhere here, somewhere around here. as you go to faster rotating stars, these stars become more active, and the activity is here measured in terms of the mean field strength in the photosphere, which is derived from Zeeman broadening of spectral lines. So the sun become more active for about an order of magnitude in increased rotation rate, but then they seem to get into the saturation regime where the activity does not depend that strongly on rotation rate anymore. At least this regime of getting more active stars as you increase the rotation rate, this is also seen in 3D simulations. Here they also studied suns or solar-like stars with different masses, different rotation rates. They show generally the same trend that activity goes up something by an order of magnitude when you increase rotation roughly by an order of magnitude. So that part is more or less consistent in general terms. Interesting thing is what happens as you go into the saturation regime, and I think this is not fully understood. This is really a saturation of the dynamo itself, that in some way Lorentz force feedback prevents building up of stronger field. It could be also simply an effect that the photosphere at this point here, once you hit this point here, right, this is an average field strength of 2000 Gauss, 3000 Gauss. It's pretty much like having a sunspot umbra everywhere in the photosphere, right? At this point, you produce so much large-scale field that you pretty much filled up the entire photosphere with sunspots. It might be simply a saturation due to space constraints. You just cannot put more flux into the photosphere. That causes this trend to kind of taper off here. One other thing people also observed is, and that is kind of highlighted in this plot, is that as you go from slow rotators to fast rotators, that the magnetic field becomes actually more complicated. Kind of these big round symbols indicate more simple magnetic field configurations, whereas the star-like features here, they indicate a more complex magnetic field topology. So two things happening here. You get more flux produced on the large scales as you go to fast rotation, but also the magnetic field topology is more complicated. The sun has a property that during solar minimum, the polar caps have pretty much more or less unipolar field. These fast rotating stars very often have a strong mixed polarity component, even at their polar caps, which makes the magnetic field much more complicated. Okay, one other interesting part is the overall rotation evolution of stars throughout their lifetime. And this plot on the left here shows kind of the evolution, rotation evolution of stars kind of from the early star formation through their main sequence phase towards the end phase when they essentially turn into red giant and finally end their life. Young stars always start with very fast rotation because when the gas cloud collapses, you spin them up quite dramatically, having rotation rates just of a few days here. Initially, these stars keep their fast rotation in the first few 100 million years before they start slowing down. And that has to do with the fact, even though they have strong field, it looks like the field is very complicated. They have highly multipolar field, which make it a very inefficient coupling of this dynamo field to the stellar wind, which makes the angular momentum loss less efficient. But after they get older, beyond a few 100 million years, they get into this very efficient spin down. And this follows some well-established laws, which were first discovered a little bit over 50 years ago by Andy Skumanec, actually here at HEO. But the interesting thing, and that is something which was very recently only discovered by actually looking at all the observation from Kepler, where they monitored the properties of stars for a couple of years with very precise photometry to both study exoplanets, but you also can study stellar oscillations. So through astroseismology, you know these stars pretty well. You can establish also their rotation pretty well. What people found is that at later times, these deceleration actually becomes less prominent. They have some weakening breaking phase, and this is actually shown here this is kind of the standard model, what you expect based on these Comanche laws. But once you get for solar-like stars to something like, which is just 90% of the solar Rossby number, suddenly this braking becomes less efficient. So it looks like that the sun just falls into this transitional regime. In that sense, it's not the most typical solar-like star. It's really a star which is at the end of this efficient braking phase, and the sun already has an angular momentum loss, which is an order of magnitude or so less efficient than it should be when it is already there. So based on this, you can already get an idea that maybe if you study the sun, we see a star which is already in a kind of a transitional regime and not the most typical phase. And this is also evident if you put, for example, the solar cycle period, which is here, into context of all the other stellar cycle periods. There's this general trend that cycles become longer as the rotation period becomes longer. Some stars have multiple cycles. There's these two branches, but the sun doesn't lie on any of them. It's kind of in between. And the current understanding is really what's happening as stars evolve. At some point, they kind of move off this branch. Depends on the stellar type. If you have the more massive stars, they turn off earlier. For the solar-like stars, the turn off happens roughly here, and the sun is roughly in this transition phase. But also is found is when you look at the cycles of these stars, if you are in this part of the domain, you do find more or less regular cycles on these stars, somewhat similar to the solar-like cycle. If you pick a star which is more close to this transition, we have now some observations which really show stars which transition from a cyclic behavior to something which looks like a grand minimum, like the sun also had. And then if you go really to stars which are at the end of this transition, they show mostly flat activity. So again, indication the sun is in some intermittent regime here with grand minima due to this transition in the behavior. Okay, I have a few more minutes to quickly talk about something very different, the geodynamo, and mostly contrasted with all these stars. What do we know about the geodynamo? So let's first look at the structure of the Earth. And we are living out here on the Earth's crust. Then you have the mantle, which has a very low conductivity. And then we have the iron core of the sun, which consists of two parts. We have the outer iron core, which is liquid, the inner core, which is solid. And we have this transition phase between mantle and core, which is corrugated somewhat. People find it might be a layer with a thickness of 250 kilometers. So compared to all these stellar dynamos, which have magnetic Reynolds numbers of 10 to the 9, 10 to the 10, the magnetic Reynolds number for the geodynamo is actually pretty moderate, something like 300, which is interesting because if you do the kind of 3D simulations we can afford these days, you can do a magnetic Reynolds number of 300. So when you do a geodynamo simulations, you don't have to worry about small magnetic scales you cannot resolve. You can resolve everything which is there. Now, the other thing is that compared to the sun, which is kind of at this transition between weak and strong influence of rotation, the geodynamo is completely in this regime of really strong rotational influence. So the Rossby number is 10 to the minus 6. And what you end up with in this regime is more or less convection rods, which are aligned with the axis of rotation, alternating, spinning clockwise, counterclockwise. And you do have some flows which are aligned with these convection rods due to breakdown of this geostrophic flow balance between Coriolis force and pressure forces. They break down at this interface between the core and the mantle due to viscous stresses. It's an Ekman layer which is forming here. And people think that some of the longer term evolution we see with the geodynamo might be related to that actually these boundaries evolving on timescales of the mantle convection. The geodynamo has very little differential rotation, so it's generally mostly an alpha squared dynamo resulting from these rotating columns with metallicity. And another interesting thing is that the geodynamo has a magnetic field which is much stronger than the equipartition field strength. It's in a strong field regime, which can happen when you're in this fast rotating system, because you get a balance between the Lorentz force and the Coriolis force, not any longer between Lorentz force and advection forces. So what sets up actually this flow pattern, and this is related to Ekman pumping, like all of you know this experiment, you have a cup of tea with some tea leaves and there you spin it. The tea leaves end up kind of at the bottom in the center. The reason this happens is you do have the centrifugal force here, which is balanced by a pressure force. You have higher pressure outside, lower pressure inside. But this balance breaks down at the bottom where you have a viscous shear layer. The fluid is rotating at a slower speed in this viscous shear layer. So you have the pressure driving a flow from the outside towards the inside, and that collects the tea leaves here. You have something similar in high and low pressure systems in the Earth's atmosphere, or these rotating columns in the outer core of the Earth. The only difference is here you have the Coriolis force. So clockwise and counterclockwise spinning columns have opposite pressures. Here the clockwise spinning ones have high pressure, the counterclockwise have low pressure. So then you have this Ekman boundary layer, which is in this case located at the both ends of these columns at the core mantle boundary, leads to a breakdown of this balance, and that essentially drives the secondary flow along these rotating columns. And that gives you a metallicity, and for that you have an alpha effect, which keeps this dynamo operating. And I would like to also make here a quick connection to liquid sodium experiments already mentioned earlier. There have been quite a few of them, but there have been this one experiment which was done in Karlsruhe in Germany, where they actually made up this tank of these columns with up and down flows which had helical motions. And the way they did this, they had essentially these pipes going through here. They had an axial flow in the center of the pipe, and then they had these spiral patterns, metal patterns. So when they pump the liquid sodium through there, they get these spinning motions, and so that they get the metallicity. You kind of mimic a little bit what might be happening in the outer core of the Earth. What they found in this regime is, yeah, when they increase the flow speed of the liquid sodium above a critical threshold, they could see this increase of the magnetic field in this experiment. The seed field is the magnetic field of the Earth, which is somewhere around a half Gauss, but then these fast-flowing liquid sodium led to a dynamo effect and increased actually the strength of the field, which kind of is a little bit similar to what actually happens in the geodynamo. And this is an example of a geodynamo simulation, a 3D simulation. And unlike the sun, these simulations were already done here in '95. They produced magnetic fields which looked quite dipolar, similar to the geodynamo. And some of these simulations also showed magnetic field reversals. During the reversals, the magnetic field doesn't disappear. It's more that the dipole disappears and you have higher multipoles, and then you just build up a dipolar field of opposite direction. This is, of course, very interesting if you want to study, for example, what happens to the Earth to a geodynamo field reversal, because, I mean, the magnetosphere shields us from all the impact of the solar wind. So it's critical to know that the magnetic field doesn't disappear, but it gets much more complicated. So actually, I'm not fully aware of people actually studied how the magnetosphere would look like if you plug in something like this, but it's certainly something interesting to study. Okay, that gets me towards the end of this talk. In the first lecture, I gave you some fundamental ideas how dynamo processes work in astrophysical bodies, and then I studied now about specific applications to sun and stars. And in these applications, we have to say there have been some limited success, right? The problem is mean field models can capture many aspects, but they require some tuning due to many degrees of freedom. 3D dynamo simulations, they found many examples of dynamos, but not many of them really look solar-like. And One fundamental challenge is here, it's even a challenge to just get already differential rotation right on the sun, because that is such a critical flow for the large scale dynamo, and has to do with the fact that the sun appears to be very close to two critical transitions which happen near Rossby number of 1. The one is the transition from solar to anti-solar differential rotation. And if you put the sun into the context of stellar dynamos, there seems to be related to this also a transition where really the nature of the dynamo changes from a rather strong dynamo, which leads to very efficient loss of angular momentum, to a less efficient dynamo, which is likely dominated more by all the small scale field we observe on the sun, which has much less effective angular momentum loss. And the sun being close to this critical transition, of course, makes any simulation very critical, very dependent on details, which makes it very difficult to actually model the sun. The case of a geodynamo, there has been more success, I think, with simulations, but I say this as a solar person who doesn't know all the dirty laundry in the geodynamo community. Maybe if you ask geodynamo people, they have different opinions about this. But at least you get some of the basic properties right, but there is some debate on whether really these models get it right for the right reason, because even though these simulations, they can get the magnetic Reynolds number more or less correct with the resolution we can afford, you cannot really simulate the low Prandtl number regime and also the very low Ekman numbers, which are related to this critical boundary layer between the outer core and the mantle, which sets up these secondary flows along these rotating columns, which actually lead to the helical motions you need for dynamo action. And of course, another thing is, for the geodynamo, we only know the lowest multipoles, something like L equals 13 or so, are constrained, because any higher multipoles we cannot really observe because they're hidden by permanent magnetism in the crust of the Earth. Okay, thank you very much.
There are some simulations at the CCC with varying geomagnetic strengths,
Okay.
including one that's right at the using.
Okay, that's
I can't remember the name of the.
Glatzmeyer, Gary Glatzmeyer. Yeah.
Including the right at the.
Yeah.
The
Okay.
dipole, where the dipole goes away, right?
Yeah.
The dipole strength. There's. So they're there. We did them as a kind of a toy.
Mm-hmm.
So they're there, but it's I'm deeply suspicious because it's well into the strong magnetic field goes well into the plasmasphere,
Mm-hmm.
right? So the magnetopause, whatever you would call the magnetopause, has moved way in.
Okay.
So we need to do some even lower boundary, for a lot of those simulations, the ones that were there, the inner boundary is that, two solar radii, sorry, 2 Earth radii or
Mhm.
3 Earth radii or something like that. So you really got to be careful. You have to
Okay.
be careful. But it is kind of cool.
Yes.
There's all these these different multipolar things where you can imagine here's the auroral zone, here's an auroral zone, here's an auroral zone, here's an
Certainly you
auroral
see
zone.
auroras in
Right.
places we normally don't see them.
Chris Nunez his silly putty reconnection.
No,
Yeah.
no, I don't think I did. Saw that.
So I stole it some time ago and used it as like a outreach
Mhm.
activity. He's done it with this group, but you take a loop,
Yeah,
right? You kind of stretch the loop,
yeah,
and then you pinch the loop, and then you break the loop,
yeah,
and then you got two loops.
Yes. yeah,
So,
yeah.
gave everybody some silly putty. Learning tool, and I use it for outreach purposes. And so there's a whole Andreas Munoz Camarella
Yep.
is at Southwest Research, does solar physics, and he came up with this. And so you take your silly putty, you roll it out, you create a little loop, right? So you can imagine magnetic fields circulating around, right? You can stretch that loop all you want. The geometry doesn't change. But then if you pinch it in the middle, you break it, you now got two loops, right? And they're two loops that are kind of attracted to each other because of the orientation of magnetic field, and so they overlap. And so then they do the same thing, and then you break it again, and you break it again, and you break it again. So, and pretty soon you got a mess. So that's part of what where the silly putty comes from. I usually use that as a little outreach demo. If you stop by the UCAR booth at AGU, you might find me doing something like that to attract people and tell them about this. So, right. So we'll go into our question period. Who's got questions for Matthias?
I have a very naive question. Is there any fractal structure in the dynamo theory, or just we divide it into large scale and small scale?
I mean, the mean field theory is pretty much large scale, small scale. You don't really have any flux rope-like structure in there. That's what I mentioned, right? If you look at the sun, really an integral part of solar activity is having sunspots. So the mean field theory doesn't really deal with sunspots, just averages over them and just tries to describe what they do on average. So if you want to get sunspots in there, what people have been doing in the past is they kind of use mean field model, for example, to get kind of the large scale toroidal field, but then they put in explicit flux emergence mechanisms to actually have small flux drop from this toroidal field forming sunspots, and then through this Babcock-Layton alpha effect, you kind of rebuild the polar field, the poloidal field of the sun. So it's kind of an add-on to mean field dynamo theory, but people have kind of created these 3D Babcock-Layton dynamos, which kind of take some concepts of mean field theory, but also put in the effect of individual sunspots as well.
I just wanted to ask about something you shared early in your presentation, which was that sort of the turbulent regions of the sun have 10 to the 8 times
more conductivity than I guess, the non-turbulent regions. Does that make a big difference in the overall magnetic structure of the sun, or is the time scale of diffusion still too long that it doesn't really matter?
So actually, the magnetic diffusivity is 10 to the 8 times higher. So
Sorry, yeah,
conductivity is the
diffusivity, yeah.
opposite. Yeah, but I mean, it pretty much leads to very different regimes for the radiative interior of the sun and the convection zone of the sun, right? In the radiative interior, without any turbulence, you have essentially a diffusion timescale on the order of 1 billion years. So there is a thought that there is likely a remnant field left from when the sun actually formed, which was essentially whatever this molecular cloud had, which then eventually formed the sun, and the magnetic field it amplified from the original field of the galaxy, that something of that is still there. And that field could have survived this long. Whereas in the convection zone, since these timescales down to timescale of years, whatever was there left from the beginning has been wiped out by turbulence since then. But it's actually a little bit more complicated than that, because people also have found, even in the solar interior, there are some additional instabilities possible, which might even enable dynamo action in these strongly subadiabatic regime, where you don't really expect convection, but you might have some turbulence on horizontal shells and so, which could potentially enable some dynamo action as well. But that's still a very active field of research. There's not general agreement really what's happening, but there's a possibility even have a dynamo operating there.
Yeah, okay. Do gas giants like Jupiter and like gas giant planets also have dynamos? And if so, what's the difference between dynamos there and those at stars?
Pretty much, definitely Jupiter and Saturn do have a strong field, and I mean, there's not too much data for Uranus and Neptune because there were only 2 flybys, but they also seem to have a field, although more complicated. So the biggest difference is that the gas giants, they don't have a liquid iron core. So the region where they might have a dynamo has likely something like metallic hydrogen, and the exact equation of state and the properties of that isn't that well known, but it's generally believed they do have dynamos. The dynamo of Jupiter actually looks a little bit like the solar one in terms of the overall field properties, just scaled up much more powerful. Saturn has this interesting property that it has an extremely axisymmetric magnetic field, which is a little bit puzzling. And it's not completely understood, but what people think is that the dynamo region of Saturn is surrounded by another region which has still a high conductivity, but doesn't have any active dynamo action, that region might have a slightly different rotation than the core of Saturn where the magnetic field is produced. And then essentially what this rotation of this outer layer with high conductivity does, it kind of kills all the higher multipoles and only the dipole survives.
You talked about that there were possible like different layers sort of in the sun's interior where the magnetic field could be generated. Could you talk a little bit more about how that would impact sort of the large and small scale structure of the field that's produced?
Yeah. So, I mean, with these different layers, the main reason people looked at these different layers is mostly the profile of differential rotation, right? You have the latitudinal differential mostly in the bulk of the convection zone. Then you have these shear layers at the top and at the bottom, which have more radial differential rotation. So the reason people put a lot of emphasis on these layers is because, for example, if you have a classic alpha omega dynamo where you combine the alpha effect with shear, if you have radial shear, you get latitudinal propagation of activity out of this, which made these 2 regions very attractive. The problem is what I showed you, that you might get these dynamo waves going into the wrong direction. The other problem is if you have it only constrained to thin layers, you might get dynamo waves which have a relatively short wavelength, which is opposite to what we actually observe on the sun. So in more recent studies, people, I mean, these ideas are not dead, but people also think maybe it's more the bulk of the convection, so mostly latitudinal shear matters, because you can extract also much more energy from the latitudinal shear. And with regard to the organization of the field, so the small scale dynamo, which is mostly responsible really for the very small scale part of the energy spectrum, what we learned is mostly that that one likely involves all scales. But of course, as you go to larger scales, you make a smooth transition from scales which are not constrained by rotation to scales which are constrained by rotation. So it's really a smooth transition from the small scale dynamo to more the large scale dynamo, and how that impacts structures of magnetic field in the photosphere. So most of these kind of network structures up to the scale of supergranulation, at least if they're not unipolar, like when you are close to an active region, you have a decaying spot, some of these feed from the spot kind of is getting transported in the supergranulation, and then you have a supergranulation network of a given polarity which matches the polarity of a nearby spot. That is clearly related to the large scale dynamo, but if you're away from active regions, you do have essentially a network which is mixed polarity, and that can be produced by a small scale dynamo. Then there is this structure kind of in between sunspots and these more smaller scale field, which is called ephemeral active regions. These are kind of bipolar structures which appear on the sun. In particular, they appear in higher latitudes, right? The main sunspot cycle starts at about 30-degree latitude, the early cycle, but if you go a little bit higher latitude, even earlier, you see some magnetic flux showing up there. They're called ephemeral active regions. And some of these structures, the larger ones, they follow the same polarity rules the sunspots follow. So they're likely part of the large scale dynamo, but there's a population of smaller structures which are pretty much random. And some of that could be simply due to the small scale dynamo.
That it could be the case that the large scale dynamo and small scale stuff are pretty sort of in like different.
Yeah, I mean, as you go to the deeper parts of the convection zone, they're more rotationally constrained. You expect more large scale dynamo action coming from that, but it's not, you cannot draw a clear line in between this, because I think what we know from observations is at least the sun seems to have a large scale dynamo which really distributed over the convection zone. You have likely the omega effects, the shear from differential rotation happens somewhere in the bulk of the convection zone, but all the regeneration of the poloidal field might be related to the active regions coming to the surface layer. So some of these processes happen there. It's really distributed dynamo, which is not just working in a particular region. It involves the whole convection zone.
I just wanted to ask, so amongst the rocky planets, there seems to be no clear pattern in terms of mass or rotation rate as to which planets have internal dipoles that are still active, at least. Like Earth is the fastest spinning and the most massive and has a dipole, but Mercury is very slow spinning and the least massive and has a dipole, but the intermediate ones don't have any active dipoles. Is there another pattern that I'm missing, or is it just not really understood why this happens?
I don't think it's fully understood why this happens. I mean, right, the two interesting ones are Mars and Venus. The problem with Venus is that there is not really any record of what Venus did in the past, because there were only a few, I mean, probes which survived there for a very short time to do likely some measurements. And unlike the Earth, where we really have this record of the last billion years due to plate tectonics, for Venus, the one problem is the surface temperature is so high that you're pretty much almost at the Curie temperature, so you kind of destroy any permanent magnetism. There's also evidence that the entire surface of Venus was redone in some recent history, I don't know, 100 million years ago, which also would have wiped out all records. So for the Venus one, there's simply not much data to know anything what that planet did. For Mars, right now it looks like Mars only has kind of magnetism also of the crust. But since that is so strong, people certainly think that likely in the past, Mars had a strong dynamo, which originally led to the magnetization of the crust. Now, if I'm not mistaken, I think one difference between Mars and Earth is that Mars doesn't have an inner solid core, but Earth does have, but I might be wrong. I'm not a geo or planetary person. But the reason I'm bringing this up is, at least for the Earth, people think having this transition from a liquid core to a solid iron core is actually critical in driving the dynamo. I mean, a planet like the Earth, unlike the Sun, where you have nuclear fusion and have an energy source, and you have essentially these enormous energy transport which drives convection. For a planet, you don't have this. You have an energy flux due to the general cooling of the planet. You have some radiative decay, which produces some heat in the interior, but it's generally believed, at least for the Earth, that this energy flux is not sufficient really to drive strong convection. So what's happening is actually the iron core, the outer, the liquid one, has iron, but it also has some lighter elements in there. And when you get this phase transition to the solid iron core, the iron is essentially making this phase transition to the solid core, and all the light elements are left behind. That leads to an overabundance of lighter elements, which then through buoyancy drive convection in the outer Earth core. So if that is really the dominant driver for convection in these metallic cores, then it would be critical to have an inner solid core and have this phase transition. And I might be wrong, but I think Mars doesn't have that core. That might be one reason why Mars may have had a dynamo early on, when it was still much hotter in the center. It had much more energy flux, but then maybe cooling off and becoming an old planet that just became too weak to maintain a dynamo and doesn't have these inner core which can drive the dynamo action still in the case of the Earth.
Could you elaborate a bit on the galactic dynamo and the connections that it may have as another fast dynamo to the sun?
So in the case of the galactic dynamo, I mean, the general belief is the mechanism which really produces dynamo action in the galaxy is kind of supernova explosions, which then during the expansion, they start rotating, and that is kind of replaces the convective bubbles in the convection zone, and they so that produce an alpha effect which maintains the galaxy. One other aspect which is different in the galaxy is that it's actually a dynamo operating at a very high magnetic Prandtl number, right? In all the stars, we have low magnetic Prandtl number, but the Prandtl number of galaxies are enormous. I don't know what they are. I thought it's 10 to the 20 or so, if I'm not mistaken. And in general, in a high Prandtl number regime, it's very easy to excite dynamos. It's sometimes more challenging in the low Prandtl number regime. So that's essentially the main difference in galactic dynamos. Whether they have a small-scale dynamo, maybe. There's a lot of maybe small-scale turbulence too, but I don't know if anybody ever brought up the idea of small-scale dynamo and the concept of galaxies. I don't know.
Pass the box back.
So while I understand there is a coupling between small scale dynamos and large scale dynamos, is there any study done on like the role of small scale dynamos, the potential role of small scale dynamos in bringing the sun back out of these grand minima kind of episodes?
I mean, certainly the small-scale dynamo would, since the small-scale dynamo pretty much all the ingredients you need to make it happen is turbulence. I mean, there's no reason to believe that for some reason the turbulence would disappear in a mono minimum. The small-scale dynamo will just stay on the same level. But if you have only small-scale field, it actually, if you try to seed a large-scale dynamo with magnetic field, which is only organized on very small scales, it might still take a long time for it to grow out of a small-scale field. So I think it's likely not necessarily the small-scale field reactivating the large-scale dynamo, but it certainly could do due to random fluctuations, because the small-scale dynamo has some organization on the scale of supergranulation. At least it might even have on larger scale. So eventually that would be enough to restart a large-scale dynamo. But to the best of our knowledge, while the large-scale dynamo was very weak during the solar grand minimum, at least observations we have still indicate there were once in a while some sunspots. So there was still some large scale component in there as well, which is likely more efficient in starting a large scale dynamo up again, because from the small scale feed, you have to, right? If you just put in a small scale random feed on the scale of the sun, and you do a power spectrum of this, you have some power on large scales, but that is extremely low power. So the large scale dynamo would have to go to several e-folding scales to bring that one back up. So if you have some very weak random feed from the large scale dynamo left, it's likely more efficient restarting it.
Thank you.
So sometimes when you look at the solar cycles over time, you can sort of see this larger modulation, like a 200-year cycle. People sometimes call that the Gleisberg cycle. Do any
Yeah.
of the models of the solar dynamo show like a larger modulation to the regular, I guess, on average 11-year activity cycle?
Yeah. So that comes to the interesting question, really, what is the main reason different cycles have different strengths? And if you just go by what observations tell us, I mean, it looks like it's kind of this backward-latent surface alpha effect, which seems to regenerate the poloidal field. Now, with this sort of alpha effect, active regions which emerge close to the equator have a much more impact than active regions which emerge in high latitudes. Because if you emerge a bipolar active region in high latitudes, you pretty much just transport both polarities to the pole, and in the end, they just compensate each other, and there's no net flux left. But if you emerge an active region closer to the equator, you have a much higher probability that the leading polarity, which is closer to the equator, actually reconnects across the equator, and then the trailing polarity adds to the polar flux. And some of the longer term variability, or why different cycles have different strengths, might be due to active regions which emerge late in the cycle close to the equator, and maybe have even, which happens once in a while, have the opposite polarity, anti-Hale active regions. And they make a dramatic impact on the polar fields, because if you think about it, the strength of the polar field, the flux we have in the poles, is not much larger than the typical flux of an active region. So if you have one active region with the wrong polarity late in the cycle, that can throw this off quite a bit. So it's believed that a lot of the cycle-to-cycle variability comes from these active regions which kind of emerge late in the cycle. And people have done these models, kind of have a weakly, just barely supercritical backward-latent dynamo with some random noise due to these active region emergence. And you can kind of estimate what is the amount of random noise you expect from the known sunspot record. And if you plug this in, you can kind of construct from this a power spectrum, how much variability you expect on all the scales. And this power spectrum looks very similar to the observed one. So it looks like this is enough to at least explain this in a statistical sense.
I'm more interested in the dynamo for planet, so I'm wondering, does the current dynamo simulation on the planet can simulate some features like the reversal period or something else?
I mean, I think it's like the reversal period, and so kind of, right, the geodynamo has kind of polarity for a couple 100,000 years, and then a reversal in 1,000 years. I think it's likely still a big challenge for these planetary dynamo simulations to simulate hundreds, thousands, if not millions of years of evolution. So I do know that some of these simulations did show polarity reversals, but if they can reproduce the right statistics of that, I'm not sure. And I'm not really working in the field of geodynamo, so I can only give you kind of the top level picture here, not the details.
Marco has a question.
I may have missed it because I had to step out a couple of times, but there was a recent paper in Nature I think it was Nature Astronomy, magnetorotational instability in
Yes.
the. Did you mention that, or do you have any ideas about that? Do you have thoughts about whether it's a relevant calculation or not, and whether MRI could actually play a role in the surface dynamo?
I mean, I didn't mention it explicitly, but I touched on a little bit that, I mean, one general problem I see with any sort of dynamo which works in a thin layer, you typically get kind of a latitudinal wavelength, which is related to the thickness of the layer. And that can be pretty short if you do it for a near surface shear layer, right? The observations tell us this butterfly diagram, I mean, it's pretty wide, right? So observations tell us we don't have evidence for really short wavelengths. And so the one challenge with anything which is restricted to a thin layer is very often that you get these very short wavelengths. The sun doesn't seem to have, and you get several overlapping cycles at any given time, but the sun has very small cycle overlap. But nonetheless, I think having magnetorotational instability in this shear layer, it's a very important, could be a very important ingredient to just maintain this shear layer in the first place. I mean, one general problem is typically you get the near surface layers angular momentum transport, which is inward directed, which in principle should set up a near surface shear layer, but very often in simulations it doesn't, because what you also do, you drive a meridional flow, which pretty much compensates these angular momentum transport and wipes out the near surface shear layer. So you have to kind of slow down this meridional flow, and perhaps a magnetorotational instability could provide an additional source of enhanced viscosity, which limits the flow speed of the meridional flow, and through that enables actually the formation of a near surface shear layer. So through that, I certainly think that might play an interesting role. I mean, certainly should look more into this, but I always have the feeling having the dynamo completely restricted to this layer might not be what the sun is doing, which doesn't mean it doesn't play a role, but it's only part of the picture. That is my impression.